Avant de démarrer, donc l'idéal serait de faire un petit tour de table, au moins pour les rapporteurs et les examinateurs. Comme ça, au moins, vous connaissez un petit peu les personnes qui sont là. Donc, first, we have je regarde, Robert Trehaft. Yes, yes, perfect. Yes. Could you please give a short presentation?
About what?
About your job, your company, your institute. Yes, no.
Okay.
Very quickly.
Okay. I'm Robert Trehaft. I come from JPL in Pasadena. JPL is the Center for Robotic Exploration of Planets. I work on this planet, on Earth. I do remote sensing development for forests, mostly tropical, but some boreal forests as well. And I'm very happy to be here. Thank you for inviting me.
Merci, thank you. Donc ensuite, il y a Jordi Inglada, qui vient du CESBio CNES. Please.
Voilà, Jordi Inglada, ingénieur CNES, donc l'Agence spatiale française, et chercheur au CESBio, au Centre d'études spatiales de l'aviation. Je travaille sur des séries temporelles, c'est-à-dire d'optique rares, pour l'observation des surfaces continentales.
Merci Jordi. Ensuite, donc le deuxième rapporteur, donc. Parce que, bon, j'ai découvert que j'étais président en mangeant, hein, donc excusez. Bon, après, il y a Jérémy Sublime, c'est ça?
Oui, c'est ça. Donc, Jérémy Sublime, enseignant-chercheur HDR à l'ISEP, et je suis spécialisé en intelligence artificielle, en particulier apprentissage non supervisé appliqué aux images. Ravi également d'être là.
Voilà. Alors, après, je continue de lire. Le directeur de thèse, c'est Régis Gernbach. C'est bien ça? Oui, c'est ça. C'est bien. Si tu as envie de dire deux mots, n'hésite pas. Peut-être les gens ils te connaissent, mais bon.
Voilà, bah, Régis Gernbach, je suis professeur à l'école et puis j'encadre avec mes collègues la tête de Thomas.
Okay. Donc, Élise Collin, co-encadrante de la thèse.
C'est ça. Moi, pour la partie ONERA, au département traitement de l'information et système.
Voilà, et puis il y a Laetitia Thirion-Lefebvre, deux mots aussi.
Je suis au laboratoire Sombrin avec Régis et je suis professeur à l'école. Et avec Élise et Régis, nous avons encadré cette thèse. Merci aux membres du jury d'avoir accepté.
Merci donc à tous. Donc,
et celui qui est à distance, je vais me faire un projet, André Baudouin, qui a la ressource naturelle qui est à distance.
Oui, il n'est pas connecté là.
Bah si, il est
oui, je suis là. Bonjour.
Bonjour André.
Oui, donc chercheur scientifique, développement d'applications forestières à l'aide d'imagerie satellitaire SAR et optique.
Très bien, merci. Donc là, on va démarrer. Donc Thomas, tu as, on va dire, 45 minutes. On n'est pas à 5 minutes près. Et puis après, une fois que c'est terminé, on enchaîne les questions. Les questions-réponses. Voilà, à toi.
So that's great. Welcome everyone, and thank you for everyone in the audience. I'll be doing this presentation in English for obvious reasons. Thanks for everyone in the room, but also everyone who joined online. So today will be the presentation of 3 years worth of work that I undertook in Sondra Lab and ONERA. We've already had a look at my supervising team, but I'll just redo a quick round check. So there was Professor Régis Gernbach from Central Supélec Sondra Lab, Laetitia Thirion-Lefebvre from Central Supélec Sondra Lab as well, Élise Collin from ONERA, and André Baudouin, who was from Natural Resources Canada. And so this presentation and the manuscript and my work in general is entitled Unsupervised Deep Learning for Vegetation Monitoring using C-Band SAR time series from agriculture to boreal forest. So if we were to jump right into it, the main focus of this thesis was on vegetation monitoring, and obviously the interest of doing vegetation monitoring are plentiful, but there is some significant difficulties when it comes down to such applications, and they are to be considered. For a very simplified overview of why these difficulties exist, so if these 100 square were to be the Earth's habitable land, well, you would have 46 of them that would be composed of agriculture. 38% of Earth habitable land would could be considered as forest. 14% as shrub, and then only 1% would be composed of built-up lands and fresh water. So just looking at these numbers, you can very easily see that to monitor such large spans of land is hardly doable while remaining on land, but hopefully we can rely on satellite technologies to ensure this monitoring for us. And we're in luck because since the late 70s, we've seen an exponential growth in the amount of sensors, plenty of technologies, but there's one in particular that we're going to be focusing on today, which are the SAR sensors. So let's just introduce what's a SAR sensor. So a short introduction on SAR imagery or synthetic aperture radar imagery. So this is a SAR image. It might be kind of like difficult to appreciate its content, so I gave you a hint on what's inside. So in this image in particular, you have a forest area surrounded by some lakes and some tracks. It's not obvious on first sight, and that's for a specific reason. It's because SAR imagery, or radar imagery in general, relates to two specific metrics when it comes down to the image scene. So first, radar imagery is highly related to the geometry of the image scene. Mainly, radar imagery relies on what we like to call active sensing, meaning that it emits its own electromagnetic waves, and the interaction the waves have with the ground is directly connected with the geometry of the ground. The second parameter is the permittivity, which measures how much this wave is bouncing on the ground, and the amount of bounce is directly related to the water content of the ground, which hopefully sounds like, well, not, because these two parameters are ideal for the monitoring of vegetation, but the geometry of vegetation, if we're able to measure it, is a direct measurement of the state, the growth, and the health of the vegetation alongside its water contents. But vegetation remain living organism, and living organisms are evolving. So the monitoring of this evolution is much more interesting than just just an observation at one specific instance. So that's why we went away from analyzing single imagery, and we went towards the idea of analyzing multi-temporal imagery. There's just one specific trick here. If you may have noticed in the title of my manuscript or in the title of this presentation, I do not really mention multi-temporal imagery, but rather I mention time series. Time series would just be, if you were to isolate a single pixel within this multi-temporal imagery, this pixel would undertake a certain amount of changes. These changes in radiometry over time would directly relate to changes in the vegetation. These changes can be changes in geometry, changes in water content, and so thanks to this temporal analysis, we're able to perform very accurate and acute monitoring of our vegetation. So now, this is kind of like the theory, but in practice, we need to be relying on specific satellite technology. And our choice was, how to say, pretty easy in a sense that we have nowadays, and we're in luck, one specific key asset for the monitoring of the Earth, which is the Copernicus constellation. And out of all these constellations, you have the Sentinel-1 satellite, which is an ideal candidate. And I will just explain to you why. So first, it's a C-Band SAR satellite. And one of the very specific aspects regarding this C-Band SAR satellite is that it's open data, meaning that anyone can retrieve imagery, process imagery, and use this imagery for its own purpose. But that doesn't stop here. It also helps to perform global coverage, as you have Sentinel-1 imagery all over the globe, almost. But also, and this global coverage has a very short revisit time from 6 to 12 days, which allows for a continuous and very high temporal dimensional monitoring of vegetation. So this is very good, like we're in luck, because in this exact context, we've never really had such great configuration, and such great configuration unlocks an unprecedented amount of vegetation temporal information. This amount of big data information is ideal for state-of-the-art processing algorithms, which are deep learning algorithms. Unfortunately, most of them rely on some labels for training or for application purposes, and we do not necessarily have these labels, as we'll see right now. As I mentioned earlier, we are really focusing on the application of vegetation monitoring. In particular, as I presented earlier, two specific bodies of vegetation are of importance. The first one is agriculture, and tons of challenges arise as soon as you're trying to deal with agricultural labels. The first one is, you have large amounts of labels, that's a fact, but most of them are closed data, meaning that you have various entities to whom these labels belong, and it's hard to retrieve them at scale. But whenever you achieve to retrieve a significant amount of labels, they are often hardly interoperable between sources. They might have different granularity when it comes to describing the crop type or the harvesting practices. So these two challenges are why dealing with agricultural labels is not as easy as it sounds. And then we have the second application body, which is the forestry application. And in forestry, you have what I would like to call two main difficulties. The first one is you often have quality difficulties. I will take the example of one of the most popular forest products when it comes down to its monitoring is forest land cover products. They often lack precision just due to the fact that they are actually generated using satellite imagery. But whenever you get your hands on good quality measurements, often they lack quantity. For example, the very precise handmade measurements that you can have when it comes down to forest monitoring are often very scarce. And so you have to come by with both of these limitations. And turns out that deep learning does have a solution to this. We just have to switch from the usual supervised deep learning approach to the unsupervised deep learning approach. And for this, well, we just went down the road of a simple algorithm called the autoencoder. It's a fairly simple when it comes down to its structure. It has two main components, an encoder, which takes a vector input and try to project this vector input onto what we like to call an embedding layer. This embedding layer is a low-dimensional space, and due to this low-dimensional projection, the intuition is that the encoder is able to extract relevant features out of the input. And then you just have the decoder, which does kind of like the inverse task, which is to reconstruct from this low-dimensional projection the original inputs. And you may have guessed it by now, the objective, the training objective for this simple network is just to minimize the reconstruction error, meaning that you take your input, you project it to a low dimension, and you try to reconstruct it as best as you can. And so this is represented by the mean square error loss between the inputs and the reconstruction. But if you've paid attention, we are not dealing with any kind of data. We are dealing with satellite image time series, which are sequential in nature. So it wouldn't make sense to take advantage of this sequentiality. And this is precisely what we've done. We've moved away from the usual autoencoder towards a more convolutional autoencoder by adding convolution layers as relevant feature extractors. To make sense of what these one-dimensional convolution layers do, a quick flashback on the convolution operation. So given an input signal and given a parameterized kernel, you just apply the convolution operation at each time step of the signal, and by this means you extract some relevant features. It's even more true whenever you add and stack convolutional layers one after the other, you get more dense, more complex convolutional features extracted. And so thanks to this, we have this approach, which allows for the extraction of temporal patterns from our input time series. It has many advantages among the ones I quoted here, which is it's invariant to shifts. Whenever you have an event happening within your input time series, if a shift happens temporally, it should be invariant to it. It's more robust to a phenomenon called temporal speckle, which happen in our time series. And thankfully, it's much faster and much more parallelizable than the regular fully connected layers. So I've been exploiting this approach in various contexts. And so this is how I will go through each of them. So first, I've performed an applicability assessment of this autoencoder to the study case of agriculture, namely doing classification and level anomaly detection. And then I moved on to more forest-focused applications, up and down to the application of modeling forest diversity. But first and foremost, let's dive in the agricultural application. And so for this, I wanted to say special thanks to Dr. Juan Manuel Lopez Sanchez, who provided us with both the Sentinel-1 and the ground truth data, which were crucial, obviously, for the well-doing of this study. And so here we've been focusing on a specific agricultural area near Sevilla in Spain, where we have 1 year of Sentinel-1 intensity data, meaning that we have 61 separate SAR acquisitions, and each of the time series within these acquisitions is labeled with 1 out of 16 crop types. These crop types are categories of various specific crops that are harvested over the area. And it turns out that if you were to look at each of these crop types and see their radiometrical profiles, you would be able to see some specific temporal patterns. You see that the crucial periods defining what a crop type actually looks like, which are the growth, harvest, and seeding period, are all identifiable for the majority of the crops. And you see very concrete illustrated contrasting practices between crop types, which result in very different profiles. So I mentioned earlier that you do see various steps. So for example, I overlaid the temporal signature of cotton with the various steps cotton undergoes when it comes down to its harvest. And so you have the various steps, which is sowing, full cover, senescence, and harvesting, which are clearly identifiable directly within the Sentinel-1 time series. So the question is, well, if it looks like we will be able to differentiate all of these crop types based on their average temporal signature, would an autoencoder behave as expected when confronted with such data? And so more specifically, we've defined two objectives when it comes down to the application of the autoencoder to this particular use case. The first one being that we want just to validate its usage. We want to make sure that it behaves well and accordingly to our expectations by comparing it against other approaches, which would mostly serve as baseline. These approaches could be unsupervised and supervised, as you will see, but there's also something else. Turns out that actually the autoencoder is parameterized by a key parameter called the embedding size. I mentioned earlier that the embedding dimension is just a projection space that is computed by the encoder, and choosing the dimension of this projection space is a direct influence on performance. And so we wanted to estimate this influence and estimate the performance drawback we would have when it comes down to choosing embedding dimension sizes. For the sake of experimentation, we've developed just a pretty simplistic approach. We just have our input SAR time series. We're processing them with the convolutional autoencoder. We generate a list of embeddings, and each of these embeddings are clustered into a specific cluster for the sake of attributing classes to these embeddings. The intuition here being that if some input time series are located close to each other within the embedding space, they are supposed to belong to the same class. And so following this approach, we're able to evaluate the value, the quality of the embedding space. And then, last but not least, the class assignation process relies on the cluster-specific majority vote, meaning that within a cluster, we just do a majority vote of which class is the most common. And then we assign this class to the rest of the cluster. And so following this pipeline, we have a list of crop type affectations at the end, and we can very quickly, based on these affectations, compare with the ground truth data and obtain some scoring. So here we're able to meet the expectations of the first objective, which is to validate the usage of a convolutional autoencoder by comparing it, as I mentioned earlier, against other unsupervised approaches, as well as against supervised approach. So when it comes down to ranking within the unsupervised land, it turns out that the convolutional autoencoder beats the other competitors, which include the normal autoencoder, which doesn't rely on convolution as a feature extractor, but also the more common and obviously less elaborate linear PCA. But then when you are comparing the score of the unsupervised approach against the supervised approach, obviously you are lacking some performance. But the gap in performance is not that significant in the sense that it appears that the convolutional autoencoder is able to encode enough information within the embedding space so that we're still retrieving crop type in some ways. But this is just the first objective. We still have the study of the impact of the embedding size. And here we are seeing a plot where we plot the embedding size against the performance, namely the overall accuracy. And we see that the same observation stands for all three of the configuration, all three of the algorithms. The higher the dimension of the embedding space, the better the performance. And so based on this is kind of like an overall study. This is just an overall oversight of what's going on. But if we were to dive inside the performance metrics by relying on confusion matrices, we would kind of like see the smaller picture, which is actually kind of interesting here. What's the change in behavior of the embedding space between the one-dimensional all the way up to the highest dimension, which is the 20-dimensional embedding space? Something very easy to see is that more and more crop types are actually retrieved. You don't necessarily have a better performance for the crop types that are the most popular. So, for example, the cotton, tomato, and sugar beet crop types. they are all retrieved in the same fashion, no matter if it's a one-dimensional or 20-dimensional autoencoder. But then when you move on to new crop types, maize, wheat, sunflower, they all become much more retrievable the higher the dimension. And this kind of makes sense because by relying on a higher dimension, you have more space, if I say so, to put your various crop types, to assign your various crop types to specific locations within the embedding space, and it's much more retrievable by the clustering approach. So this is kind of validating the usage of the convolutional autoencoder, and as well, it's also displaying the direct impact of the embedding size. But there's something going on actually. If you paid attention to some slide earlier, you may have noticed that there's some confusions that don't really make sense. Sugar beets and cotton, they are obviously nowhere near each other. And so if we were to just, as a reminder, compare the temporal profiles between the two, there seems to be some confusions that do not make sense. There's no way we could confuse cotton and sugar beets. Considering they are both in high quantity, that they both have very different distinctive temporal signatures. This confusion comes from somewhere else, and so we decided to investigate where this confusion could come from. So for the sake of this investigation, we relied on a two-dimensional embedding space, which allows for very simplistic plots, just a scatter plot of the two projection dimensions on the two axes, and then you have this point density coloring, which allows us to locate where are all the time series located within this embedding space. And very quickly, we're able to identify 4 separate clusters that are here identified with those 4 separate colors. And when we are plotting the temporal signature of each of these 4 clusters, something very fun appears, is that 3 out of 4 of them is actually not cotton profile. So there's something going on. Labeled time series labeled cotton are actually not cotton at all. So it turns out that the dataset labels that we are relying on, they are riddled with errors. And the main thing is we would hope for the autoencoders to be able to detect them and potentially to correct them. So these errors are quickly identifiable by the eye and relying on optical imagery, as you can see on the right. But we would want something much more automated, and thankfully the autoencoder is a way to go when it comes to automation. We've relied on a specific, we've changed kind of the way of using the autoencoder here. We've relied on a specific new approach, which is what we like to call the class experts convolutional autoencoder. So given an input, a multi-class agricultural data set, we are just splitting these data sets in n categories, n being the number of classes. And we train a specific autoencoder on each of these classes, and each of them will be considered as a class expert, hence the name convolutional autoencoder. And then once we've trained our approaches, we are just able to generate what we like to call the reconstruction vector, which given an input x, an input time series x, generates the reconstruction for each of these class experts convolutional autoencoder. And then intuitively, what should happen is the minimum reconstruction value should be made by the autoencoder that is the same class as the input. If it's not the case, something's wrong, something is going on, and this is precisely what we've done. So given here that we have an input x, where the minimal reconstruction value is performed by the convolutional autoencoder 2, we just check where, well, is x of class 2? If it's not the case, then we label it as suspicious and we set it aside. If it's indeed of class 2, then we've matched with the labels, and so we're able to say that this specific example is actually trustworthy. Following this practice, we're able to identify all the suspicious crops within the area, and then we are just able to relabel them. So for metric performance, we have 2 key metrics that are kind of making sense in the applicative contents I illustrated. The first is the amount of correct relabels, which is actually, in my personal opinion, one of the most important here, meaning that if you were to change labels of a given data set, you have to ensure that this change is guaranteed to be true. You don't want to be introducing errors. So the amount of correct relabels is precisely this. It checks how many times do you make how reliable a correction is. And then you have the second metric, which is just how many corrections you've performed. And so you can kind of see very easily that there's a trade-off between the two. You can correct tons of mislabels, but maybe the corrections will not turn out to be really reliable. And I find that, applicatively speaking, you do not want to worsen the situation by including more and more label errors. So that's why we are really comparing the approaches following the amount of correct relabels, which are the orange bars. And we do see that the introduced approach, which is the farm SAR approach, performs much better than other approaches, whether unsupervised with the convolutional autoencoder or supervised approaches with the random forest and standard vector machine. I didn't include the convolutional neural network because it didn't behave well at all. It overfits on the errors, so not reliable at all for this task. And so based on expert knowledge, turns out that there's approximately 10% of errors expected by the dataset makers. This is the information they forwarded to us. And when applying this approach of correcting, isolating suspicious crops and correcting them, we're able to identify approximately 5% of these errors, meaning that half of the expected errors found within the dataset were corrected by our approach, which is somewhat satisfactory. And then when it comes down to the locations of these errors, so here you can find that they are all scattered around the agricultural area, so you don't really have like specific patterns where the whole area of the agricultural data set is completely wrong. You really have this scattering of all these suspicious and mistaken labels. So this kind of justifies the use of the autoencoder in a very applicative way of extracting information from SAR times trees without the labels. And whenever you do have the labels, you can do some quality analysis of how reliable these labels are, just based on the fact that you don't rely on them to train your autoencoder. So this kind of sums up how effective it is in the context of agricultural applications. So now, as I illustrated earlier, we have a second application, which is the application to forest. A very common forest monitoring issue is the monitoring of forest fires. It's the priority of a lot of entities, and it turns out you have tons and tons of data regarding the locations, the intensity of fires. And so that's why we went down this road to validate, extend the results we had on the agricultural case down to the forest application case. We have a very simplistic approach when it comes down to monitoring changes within forests. We follow this idea that a healthy forest, has a specific signature. Over time, a forest is evolving, as I mentioned earlier. It's a living organism, so it's ever changing. But this change is actually very conditioned by the healthiness of the forest. So if you were to find and to really model what a healthy forest looks like, you would be able to model what a disturbed forest looks like. And following this idea of healthy forest versus disturbed forest, you kind of, if you were able to find and identify the deviation in the temporal profile between the two, you would be able to find disturbances. And this is precisely what we've done. We've relied on the healthy forest as a training environment for autoencoders, for what we like to call area of interest autoencoder, area of interest expert autoencoder, which are modeling the reference SAR times series of healthy forest. And then we're just applying them on locations which we assume to be disturbed to isolate and extract anomalies. And in this exact scenario, anomalies turn out to be forest fire. And which forest fire we focused on? Well, we focused on some forest fire that happened in northern Canada, in the Quebec region, forest fire, the Labrie forest fire. And so we've relied here on 2 years of Sentinel-1 acquisitions. Why 2 years? We just, in a very simplistic way of saying we have one first year, which corresponds to our healthy forest condition, which is the year of 2017. And then in 2018, the forest fire happened. And so we do have our non-healthy or disturbed forest time frame. And so following this idea, we just have a somewhat simplistic pipeline as well. We train our autoencoder to reconstruct and to model really the healthy year, which we reference here, which we designate as the reference year. And then we try to isolate the disturbances which happened within the monitored year. And so following this pipeline by computing a difference between the two, then spatial smoothing and finally thresholding of the spatial smoothing, we're able to identify and isolate forest disturbances, which here in this exact scenario kind of looks like a croissant in this case, and this of Labrie forest fire. But frankly, this is a pipeline, and we try to validate something very specific here, just the usage of the autoencoder for forest disturbance detection. And following kind of like a similar approach as earlier, we just compared its performance against other approaches, whether unsupervised or supervised. And so following as I mentioned, following the same fashion, we have here the unsupervised approach, which we relied entirely on convolutional autoencoder for the performance evaluation, because we've seen already that it's the best among these unsupervised approaches we've benchmarked. And we compare it against supervised approaches, namely the convolutional neural network classic and the random forest. And something that we do see is we have, again, the same similar observation as earlier. The higher the embedding dimension, it appears, the better the performance. And here, something very unsettling happened, meaning that we have almost equal, I didn't mention digits, but it's like near equal performance between the convolutional autoencoder and supervised approaches. So we not necessarily, it doesn't necessarily mean that we are predicting fire as well. It just means that these approaches are reaching the limits of what the sensor allows to do when it comes down to finding these fires. So when relying directly on how the images look like, so this is before the thresholding state, we do see that in all the configuration, the outline of the fire is well retrieved. You kind of have these gaps within the burnt area, which are direct influence on the eventual sensor limitations. But you can see that among all the approaches, you have a well-retrieved forest fire. But the difference between the one-dimensional and 20-dimensional autoencoder is really manifests itself here, as you have much more gaps. The prediction is much less dense in the one-dimensional condition rather than in the 20-dimensional condition. And I forgot to mention, of course, you might have noticed, but this study was in collaboration with ESA, and in particular the PhilLab and ESA. So I wanted just to thank Bertrand also for welcoming me and helping me on this research. But this is just modeling forest fires. But it's following a very simple assumption that forests are homogeneous. Turns out that forests are very diverse environments. You have tons of things happening within the forest environment. As I mentioned until now, we've really focused on two specific ways of modeling the applicative potential of the autoencoder. First case scenario, on agriculture, we're able to specify, okay, to kind of split the input time series into various crop type categories. And we've done a somewhat similar ways of splitting an input SAR time series data set into whether they belong to forest or whether they belong to burnt forest. But if we were to have a closer look at what's going on within the forest, we would probably find that not all trees look the same, not all trees are physically the same. There's a very significant diversity in physiological and physical aspects of the forest. And the question is, well, until now, we've really focused on a binary approach when it comes down to extracting value out of the embedding space, whether we belong to forest or forest fire class. What if we were to rely on a much more continuous appreciation of the information content of the embedding space? This is precisely what we've done. But before jumping right into it, I just wanted to mention that for the sake of this study, we've actually went in boreal forests alongside Régis, Laetitia, and André. So we had quite a lot of fun. We are able to, we've monitored, we've seen what forest fires actually physically look like once they happened. We've also checked how some various forest measurements are performed. And so I wanted to just reiterate my thank you to Dr. André Baudouin for welcoming us and guiding us in this tour of the natural resources of the Canadian forests. And so very quickly, so this is the area we visited with André, which is called the Parc National des Grands Jardins. I will refer to it from now on as a PNGG because it's kind of faster. And within this area, you have 75 inventory ground plots. You might notice them as these red dots scattered all around this test area. Each of these dots actually are locations where 4 separate measurements were performed. These measurements are made over 20 by 20 meter stands of forests. And I will go back on what these measurements are right after. Because there's a second study site. We're in luck. We have the Hay River study sites where, in a similar fashion, we have 39 inventory ground plots. And on each of them, we have 4 measurements that were performed, measure over 20 by 20 meter stands. I just wanted to remind that these measurements were not performed by us. They were provided to us courtesy of Dr. André Baudouin and his colleagues from Natural Resources Canada, whom I thank because they really allowed us to do this study. So thank you for your continuous support. So these are the 2 locations, and as I mentioned, we have 4 specific measurements. What are they? So we have 4. We have plenty of ways of measuring what a forest looks like, but 4 of the ones that we found to be the most relevant were the following. The first one is to measure the basal area of a tree. A basal area is very simple as well. It's a cross-sectional area of trees at breast height, 1.3 meters or 4.5 feet high. And then once you know the basal area, you can perform lower height measurements over the stand. Basically, you average the height of all trees and you weight the average by the basal area measurements. Then you have the above ground biomass. It's pretty simplistic. You take all the tree biomass above 1.3 meters high and you just sum all of it. So you obtain a ton per hectare measurement. And then you have the last one, which is also pretty self-explanatory, which is the coniferous percentage. It basically mentions how many coniferous trees you have within a specific area. And so this is measured and weighted once again by the tree basal areas. So that means we only consider trees that are above 1.3 meters high. But you may have noticed that we do not have really that many data. As I mentioned in the introduction, we have here very high quality measurements because they are handmade, but we do not have plentiful of them. So it's kind of tricky to validate that we're able to retrieve them from the embedding space. So that's why we've not really relied on the same approach as we've done before, but rather we've relied on some leave one out validation, approach, meaning that given that we have a low amount of data points, we have to find some tricks in validating that they are indeed retrievable from the embedding space provided by the autoencoder. And for this, we used, as I mentioned earlier, this leave one out validation, which in a very fast way, I will explain, it just splits in all one versus all configurations possible, the data sets, and trains one specific algorithm on each of these configurations and predicts and performs an inference or prediction on the one data point that is set aside. And thanks to this, you're able to have this ground truth versus prediction measurement, where all of the predictions were made under a test set environment. So following this, we're able to have these performance metrics, which is very, very neat. So we see here over Hay River, we have this R2 score. So as we have a kind of like a regression problem, the quality assessment of how well we do this regression is done following the R2 score metric. And here we are very promptly can isolate 2 metrics, 2 measurements that are very well retrieved. In particular, given that we are using C-Band SAR ×3, which is known not to be the best performing when it comes down to forest monitoring. We have the above ground biomass and the lower height that are retrieved with a R2 score of 0.63, considering the maximum R2 score is of 1. And then when moving on to PNGG, Parc National des Grands Jardins, we have somewhat different metrics, but we still have our winner here. The percentage of coniferous trees is very well retrieved by one specific configuration of the autoencoder with up to 0.68 of performance. Okay. But this is just some raw numbers. But what does it look like? How could we extract even more value following this approach of assessing the retrievability of forest parameters from the embedding space? That's very simple. We can do mapping. And this is kind of cool, considering that we do not rely on a lot of labeled data points to perform this mapping. We follow a very simplistic approach. We have our location, which consists of stacks of imagery. We project this stack of imagery into an embedding space, and we have trained, following the leave one out philosophy, various models to perform inference. Each of these models is just reused to generate one prediction map. So one prediction map per prediction model, which we aggregate in 2 ways. First, we have our average prediction map. We just average over all the trained models their prediction maps to obtain this average prediction map. And then we can have a prediction uncertainty, meaning that for each single point within the area, we're able to extract how deviant the predictions are among all the available trained models. And then following this principle, we can obtain results similar to this one. So we've mostly focused on the parameters that, as I mentioned earlier, were well retrieved, which are, in the first place, the above ground biomass over the Hay River region. Here we see, so as I mentioned earlier, these two maps were obtained using only 39 annotated data points. So I just want to stress this out because in terms of how much data you need to generalize the performance of the convolutional autoencoder over a largely unlabeled area, this is a great way of picturing this. So we have the above ground biomass measurements mapped on the left with the prediction uncertainty on the right. Very easily, you can kind of very quickly identify that the areas that kind of look like they have much more biomass are all located close to the Hay River, which corroborates some early observations we had and some discussions we had with André when it comes down to how this test site is actually distributed. But something else that you could actually find, which is more on the negative points, is that some locations which are completely naked of any trees, in particular here on the eastern side of the image, are predicted with having some non-zero above ground biomass. This does make sense actually, because as I mentioned earlier, we are relying on tree measurements. So we are generalizing tree measurements over areas which do not have any tree on them. So in some ways, we cannot really do a miracle as we do not have the information of what's going on when there's no trees. We cannot really generalize to this exact condition and exact situation. I would even go as far as arguing that if we were finding zero above ground biomass over these non-wooded areas, that would raise some alarms. So we've just performed the same approach. We've done this for the Lorry height prediction map. Very thankfully, we have hugely different looking maps. This is great for various reasons. The first one being that these two predictions are not directly correlated to one another. They are, but they are not exactly distributed in the same way. So finding a different prediction map is somewhat reassuring. But here we assume that the quality of this map is still lower than the one of the above ground biomass. And then when monitoring the prediction uncertainty, we see that mostly the locations where the uncertainty is the lowest are the locations where the measurements were made. And this kind of makes sense because obviously where you had measurements and where you were able to use leverage data to train your models is where you will have the lowest uncertainty. So this is all good because we do not have any wrongdoings or any anomaly going on there. And then moving on to the last test site, which is the PNGG, where we performed the coniferous percentage prediction map. So here, this map, we've chosen a slightly different color map for the simplistic reason that below 50% of coniferous covers, you just have covers of other types of trees, like deciduous trees or broadleaves. And something very easy to, very quick to identify as well is that when it comes down to uncertainty, turns out the locations where you have almost no coniferous trees, or at least an inferior amount of coniferous trees when compared to our category of trees, is where you have the highest uncertainty. Once again, makes sense. You are on distribution tails. That's where you have the lowest information. So that's where you are the most uncertain. But I kind of hid something from you until now, is that we do have some land cover product over PNGG. And we're in luck because this land cover product tells us in a non-continuous way whether a specific location is covered by coniferous trees mixed wood, meaning that it has like a somewhat equal percentage, equal amount of coniferous and broadleaf trees, or if it's dominated by broadleaf trees. If we were to use this land cover map for performance evaluation, we'd directly be able to say how well the generalization properties of the autoencoder for these specific scenarios are. But for this, we need a special trick. We can no longer really rely on this continuous coniferous percentage metric. We have to categorize each of the pixels among one of the 3 categories available within the line cover map. And this is precisely what we've done with an adequate game of putting the right threshold at the right place. We've been able to assign for each pixel, based on this coniferous percentage, 1 class out of these 3. And when overlaying the 2, we very quickly see that the prediction is it's not perfect. It's in particular for the broadleaf class, but overall we do retrieve pretty well and fairly well the locations of conifers and the locations of mixed trees, despite having only leveraged 75 annotated data points for the generation of this prediction map. And so this, in my humble opinion, is why the convolutional autoencoder and unsupervised approaches when, in remote sensing contexts are really powerful. It's because you do not necessarily need that many labels. You don't necessarily need that many labels to perform accurate predictions. All you need are powerful models and data, obviously input data, which contains the information. And thankfully, Sentinel-1 times contains enough information so that we can output such results. So we are nearing the end of the presentation. So just quick summary of all the contributions I presented, and even more, you will see. So first, we just introduced a new, in the context of SAR time series processing, approach of dealing with such input types, which is just what we dub the convolutional autoencoder. So as a reminder, we have this network, which is made of 2 parts, the encoder and decoder, and we've really leveraged the embedding space as some sort of gateway towards all the information content of the original SAR time series. We've really focused on the encoder design by adding the one-dimensional convolutions, which allowed to extract much more relevant temporal patterns than just relying on the classical fully connected layers. And then thanks to this model, we've been able to develop various applications. First one being, we've been able to use it to distinguish vegetation classes without supervision. Namely, we've been able to, I presented it in this presentation, identify crop types, but also to classify forest cover. You may find this forest cover application in the manuscript. I didn't really include it in the presentation, but we had this first applicative potential, which is the distinguishing of vegetation classes. And then we had another approach, which is to find anomalies within vegetated environments. These anomalies can take various appearances. They can be crop mislabels, forest fire. Turns out the autoencoder can handle them all. And then we had one last, which in this scenario was only applies to the case of forest study, which is to extrapolate sparse and scarce labels to perform large-scale, what we believe to be large-scale vegetation mapping to a certain degree of precision. We've particularly illustrated this degree of precision when it comes down to coniferous percentage prediction. So that sums it up for the contributions, but obviously we've left out tons and tons of potential when it comes down to the applications. In particular, we've not really dived in the complexity of why the model is designed this way, what we could do better. And I believe that tons of perspectives regards the model design, in particular adapting the training objective, the loss function I mentioned earlier, which is the reconstruction error of the autoencoder to match with the statistical characteristics of SAR data, meaning to match with the distribution, the known distribution of SAR information. We could also try different design. We could rely on the recurrent neural networks. We could incorporate the very fashionable attention mechanism. There's tons of things we can try out. Our model is pretty simplistic for the reason being that nothing was really done in the context of SAR time series beforehand. So we really prepared the field for more and more designs popping up. Then we've done repeatability and explainability investigation, but we didn't push it very far. We've just developed this GradSum tool, which I mentioned in the manuscript. But there's still this question that is left to be answered, which is how repeatable and how explainable the embedding space we generate actually is. And then last but not least, we could also have a modality shift when it comes down to designing our model for, just simply by following the multimodal approach. If we were to have a multi-branch autoencoder, which would be able to incorporate various time series, that could be various different paths, or that could be different sensors, even different sensor technology, merging SAR data with optical data, what would be going on. And these all are really ways of analyzing the potential of shifting our focus when it comes down to designing the model. We have perspectives regarding the data. Mostly it's trying out new SAR products. I didn't really dive into the complexity of what makes SAR data, but there's so much more than just intensity measurements. We could focus on coherence time series. We could focus on plyometric parameters time series. There's tons of ways of modeling what SAR data information contains that we didn't really assess within this manuscript. And I really truly believe that in this applicative context, the autoencoder would really be a great tool. And then we just have the new SAR configurations and resolution, meaning if we were to have other satellites than Sentinel-1 with other bands, other resolution, how well would the autoencoder behave? How would it adapt to this new spectral distribution, to these new geometry characteristics? And then last but not least, we have a non-exhaustive, obviously, applicative perspective list, which is we've shown the leave-one-out validation as a way of performing mapping with a low amount of labeled data points. But we really focused on a subsample of all the possible potential forest parameters. What if we were to extrapolate this and apply it on new, and I mean by new, by non-assessed forest parameters? There's tons of them. There could be the quadratic mean diameter, which is a very popular density measurements when it comes down to forest monitoring. And so there's tons of parameters that we didn't really assess. But then following this kind of idea, we could also assume we are dealing with time series. What if we were able to do some temporal evolution analysis of these predicted parameters just by leveraging multiple generations of satellite data? I've shown it in the first slide. We have actually satellites and running satellites since the late 70s, early 80s. If we were to gather all this data around and to apply the autoencoder on them, would we be able to actually generalize and extract forest parameter out of this dense pile of unannotated data? And then last but not least would be I presented the FARM-SAR approach, which is basically to diagnose the label quality within agricultural context. We could generalize this to forest applications. I mentioned that the quality of forest labels is a concern and is an issue ongoing. So that would be great if quality assessment tools would be generalizable to the applicative case of forests. So that concludes for the perspectives. And then just a round of thank yous. So particular thank you first for, again, André Baudouin from Natural Resources for all the coordination and the help and the compilation of all the Canadian data sets you've seen until there, for his warm welcome when it came down to our exploration of the Canadian woods, protecting us from white bears. That was a great experience for us. Thank you also to Bertrand Lesaut for the help and the organization of my visiting stay at SAS Vin, which really helped in the sense that it was pretty conclusive. It led to a journal publication in collaboration with the PhilLab, which is quite an achievement. So that was a great experience. And then also thank you to Dr. Juanma Lopez Sanchez for all the agricultural reference data, for the various sync we had discussing the intricacies of the labeling issues. And then last but not least, again, a round of thank you for my supervising team, Régis, Laetitia, and Elise, as well as my fellow PhD students who were at the crossroads between both Sondra and Onera. So that was great to spend. So I was spending half my time between the two labs. So jumping from the Sondra physicians to the Onera with the scientists and mathematicians was quite a pleasant experience, as well as to my family and lover for all their everlasting support. So thank you. That concludes it.
Merci. On va démarrer les questions donc avec Jordi. On te laisse peut-être 2 minutes si tu veux voir, respirer, mais pas à la tâche.
I would say in English because I know part of the online audience is English speaking only.
So, first of all, so thank you for this presentation. It was clear, and you managed to prepare a slide deck with only one equation, which is interesting for a remote sensing and data science presentation. And you showed that you have done many experiments. You have manipulated lots of data in different applications. So you covered a very wide range of application fields. So this is, I mean, this is this shows your mastery of the data manipulation, of the tools, and the different application fields. So congratulations for that. And I will start with questions. Maybe the first thing you have put this on the perspectives of the outlooks of your one of your last slides. And one thing that surprised me when I started reading your dissertation was that you're working with time series and you use one-dimensional convolutions, which assume regular sampling and also which assume fixed size of input data. And so in my report, I asked why didn't you use recurrent neural networks or attention mechanisms like transformers and these kind of things? You have put this here, but could you develop a little bit more? Because I guess that when you started your work, there were already at least a couple of papers using either RNN or transformers on Sentinel data. So why did you choose to focus on convolution and then big size architectures?
So thank you for your question. It's a very relevant question because it came from my mind as well. I've actually tested recurrent non-network autoencoder, but I didn't include them in the manuscript. This was really early testing. The performance was not as good. The embedding space was, topologically speaking, weird and behaving not according to what I would expect. So there were some behavior issues which led me to quickly ditch the solution towards a more, what I believe to be more conventional convolutional approach. As soon as I reached this satisfactory performance with the convolutions, I tried to see how I tried to push it to its limits by putting it in new unseen contexts, which were, as you noticed, the agricultural context, the forest context. And I've not really seen it fail, so I've never really had this intent of finding what would be better. But I truly believe that these more modern, in particular the attention mechanism, I'm not entirely convinced that the recurrent neural network would behave according to my expectations, but the attention mechanism surely will have and bring value to the table. But one key argument that you mentioned was if you have irregular sampling, it's not the convolutions. Then the convolution operation then no longer really makes sense as it assumes regular sampling. Empirically speaking, I've tried it when you didn't have this regular sampling, and it still was behaving well, because even if your data has gaps, as long as these gaps are not input within your model, you can still extract some information and some values, and you would have these patterns that are extracted but are not necessarily regular in time, but that are still there within the data. And as long as all your data set is homogeneous in its missing components, I assume that convolutions will behave well with in this regards.
Okay, how do you manage the fact that you may not have the same acquisition dates on all the area that you have to monitor? So I didn't fix this issue, meaning that I've only focused on areas where I knew in the first place that there would be a homogeneous. In no case that I wouldn't have similar dates.
There are various approaches I could imagine. If you had only, for example, it happens very often with Sentinel-1 when you are at the edge of the orbital tube where you have overlapping orbits. You could do the fourth, what I mentioned as the multi-branch autoencoder, which would one branch would consider a specific orbit configuration, the other branch would consider the other one, and they would merge them as separate modalities. So that's a way of still relying on convolutions while addressing the issue of having inputs of various trajectories. I've tried this out actually over some with some TerraSAR X measurements, which were performed along different trajectories, but I've not really pushed it far enough so that it finds its place within the manuscript itself.
Okay. So that means that you have to retrain different models for every area for which you have different acquisition dates.
Yeah, in this exact context, you might have, I've mentioned something I've called, for example, when it comes down to forest fire monitoring, my autoencoder as being area of interest expert. This is kind of like a fancy way of saying that it was trained on this area and would be applied on this area. So I really believe that in an applicative context, you would have a predefined area of monitoring where the autoencoder would be trained to model an expected distribution and find deviations from this expectation. I do not believe that it has the potential of generalizing to unseen locations, to unseen time series and profiles within a given location. I assume that it would behave accordingly to expectations, but as soon as you move away from the location, I don't assume and I don't expect the autoencoder to behave well, but I believe that it doesn't really match with its applicability characteristics. I really see it as a model where you have a given data set with restrictions regarding its locations or regarding its temporality, and you want to extract insight from this given data set. You don't necessarily want this model to be able to generalize and be applied to other new data sets. You really you use it as an exploratory tool to explore the information content of a given data set. And you can then extract some information which relates to forest fire, which relates to forest physiology, which relates to crop types. So obviously you don't really have the generalizability, but you do have this exploratory potential that I still find to be highly valuable for scientific applications.
Okay. Does that mean that you try to overfit the model to your data?
In the case of finding anomalies, yes, that's the point, is that you want to model as best as you can the distribution of your training data, and then so that you find any deviations from this expectation as easy as possible, meaning that you do have this kind of like overfitting objective. It's not per se an objective, let's just say that you don't necessarily try to avoid it.
Another thing which was not clear for me when reading the manuscript was that do you use both ascending and descending orbits? And how do you manage to include them both?
It's a very good question. I use either one of them, and I've tried using both at the same time. And again, I've relied on multi-branch approach, where one branch would be ascending, the other branch would be descending, basically. So I have an embedding space which contains information from both orbits, but they are not processed together. They have their specific processing pipeline with their specific autoencoding branch and decoding as well. But the embedding space contains information from both orbits.
Could you imagine to use, and then for the two polarizations, you use them as different channels of the same modality, let's say?
Exactly, yeah, and precisely.
And why not using both ascending and descending as different channels of the same modality, assuming that you have 12 hours, a 12-hour gap between the two acquisitions?
Because they don't necessarily match in the sense that you may have some gaps in either descending or ascending, which will make their alignment difficult. Second, you may want to find some conventional filters that are different for the ascending and the descending path, because they may have different geometry within the image that will be generated because of these variations in the paths. So I wouldn't want to overload the convolution layers with too much of diversity in the profiles, which would then be hard to extract. So that's why if I were to have one branch for ascending, one branch for descending, they would both be specialized in extracting temporal features for each of the characteristics of both of these orbit paths. And then I would be able to merge them very efficiently, just because they would both be very good performant for these two configurations.
Okay, so I understand that the two polarizations are considered as the same modality, different spectral bands, let's say, different channels. Ascending and descending considered as different sensors. But did you really try to use both ascending and descending? I didn't understand your answer. Did you do it, or you were just, let's say, proposing a way to do it?
I've done it with the multi-branch approach. I've done it because I have a colleague of mine who is using this idea of extracting value from the non-symmetric aspect of looking at the same time at ascending and descending imagery to find structures. And I've tried seeing, okay, would the autoencoder, how it would encode this diversity in temporal profiles. It didn't really, you could see within the embedding space that it did a merge of the patterns that are only found within the ascending and the patterns that are only found within the descending paths, but not to a point where I find it valuable enough to be included in other studies. But that being said, that would be interesting to try in some of the study areas I've done, for example, for forest fires. The more data you have, the better it is, obviously, because you're able to you're much more precise, you have much more information. So the only thing is, but this is kind of like a silly excuse, there wasn't any descending, or like there wasn't the two paths whenever I was in Canada, because it's they don't have that many Sentinel-1 satellites, and now because we've lost the second Sentinel-1, they even have less of it. So I wasn't really able to try it on the Canadian forests, but I've tried it in forests in Guatemala, which are very different, but they have the two paths.
And do you get better results than using just one, or it's equivalent?
I got inconclusive results. They were kind of equivalent, but the application I used to measure these results didn't really put the autoencoder as it wasn't in favor of using the autoencoder. So I didn't push far enough to have a.
And do you think, let's say, let's hypothesize, do you think that on forests using C-band, having both paths will bring something, some kind of diversity in the acquisition, or given the fact that you are at the bottom at the top of the canopy, you don't nearly have volume scattering? Do you think there's some diversity which can be exploited in the signal, or actually seeing from one side or the other, you are going to see more or less the same thing?
It's a very good question. The thing is, the more acquisition you have, the more measurements you have of the same environment, and in particular forests, in particular Canadian forests, they undergo drastic seasonality changes. You have the presence of snow, and you have snow melting, thawing, and etc. And so these events have a significant influence on the radiometrical profile of forests. If you include more acquisition dates, you are able to monitor these events much better, because you no longer have just one acquisition every 6 days, you have one every 3 days, kind of. And so having more information, I assume that you can extract more precise measurements.
But if I understand well, having ascending and descending doesn't give you a better, higher frequency of acquisition, because ascending and descending are the same day, the morning and the evening acquisitions. I mean, what you will have is the same date with 12 hours of gap. If I understand correctly how Sentinel-1 works. So you won't have a high frequency. You won't have 3-day frequency of.
It's a good point, but if it were morning and afternoon, it's still good enough in the sense that this phenomenon of thawing and freezing, for example, if we were interested in monitoring forest and their impact, is significant enough so that if they were to happen in the morning or in the afternoon, we would want to be able to know. And having these two paths, I believe, would bring value to the table.
This is the kind of answer that I was looking for. I had to think a little bit, but you very well. Of course, since it's not the same time of the day, you have different phenomena in your observing. This may give you an interesting signature, which allows you to better differentiate the different things. Okay. So you said you train one model per site.
Yeah.
Because of the constraint that you have on the number of dates or the having the same dates, let's say. But on the other hand, you have Sentinel-1, which has global coverage.
Mm-hmm.
Let's say that you just keep one path in order to have the same coverage, the global coverage, and therefore, you are doing unsupervised training, so you don't need labels. So maybe you could train, let's say, some kind of foundation model, which, because one of your chapters is entitled "One Model to Rule Them All" or something like this. So why not just one model? Let's say you have all the data, you have all the Sentinel-1 archive since 2015 up till now. You have nearly 10 years of data, and you may have several GPUs to train your models. So why not just you push on the button and retrain, and several months later you have just one model which is able to give you a latent space for any point on Earth.
Yeah, but like this is
it's not a real question. It's just a prompt to to let you explain, give us your opinion on this kind of approaches.
I believe this approach is to be powerful in this. It's really something that's matching with my interests. In the sense that I found that no matter how, you don't really need having labels to extract value out of satellite imagery, and there's a lot of what we like to call dormant satellite imagery that will only be looked at a couple of people that has the expertise of processing them, etc. And I truly believe that you could extract so much more value out of all this pile of data if they were automatically processed by some sort of, as you've mentioned earlier, foundation models. And it's something I do believe in a sense that it would, for example, you have some land cover mapping that cover all the Earth. What if you had an embedding space of the Earth? And that's something I would really love to work on and love to see happening. Obviously, the convolutional autoencoder, the tiny little fraction of a model that I presented today wouldn't really behave well in such scenario. There would need to be tons and tons of adjustments. But we've already seen that much more modern approaches of deep learning are dealing with huge, immense amounts of data in a very fairly well and accurate way. And this embedding space projection, which is still the core content of tons of these approaches, is good enough so that we have this latest AI tech that we use nowadays. So I do believe that it has the potential for satellite imagery as well. And if I were to add one more idea to the table is when I was in ESA discussing with Bertrand this exact topic of embedding space and latent space representation of satellite imagery. He was mentioning that he's working on something called VQA, which is visual question answering. Basically, you have satellite image, prompt question, and you have an automatic answer that is being provided. This relies on projecting to a common latent space the image and the input text. I believe that if we were able to project the Earth onto some sort of full global coverage latent space, we would be able to query the information content of the entirety of the globe solely based on a query. And this is truly doable in the sense that at a small scale it works. So I believe at a global scale it works as well. It's just now with the autoencoder presented today with something much, much more elaborate, which would, as you mentioned, support having very different characteristics of acquisition.
Just to finish, a couple of questions of maybe technical detail. If I understand, you filter your images using sliding window computing special average, I think.
This was only for the agricultural application.
Okay. Why did you choose to do this kind of filter instead of using either a classical anti-speckle filter, or do not filter at all and use spatial convolutions and learn the despeckling?
So it's a very good question. So first, this processing was not directly done by myself. It's when I received a data set from our Spanish colleagues that it was in this condition, but I didn't really question it. So I could have gone as far as saying, okay, can you send us more raw products and we could dive into it. I didn't take much time in assessing this, and I truly believe that I could have. However, on your second part, I've done, you might have seen in the manuscript, some way of designing the autoencoder in another way by including this temporal filtering approach directly within the encoding design, relying on three-dimensional convolutions rather than one-dimensional, which would extract spatio-temporal patterns rather than purely temporal patterns. Performance-wise, it didn't behave very well. I do have the slides actually, but here, this one. So I just I had so I have this, what I like to call the spatial temporal convolutional autoencoder, which takes as an input a spatial temporal data cube. And so I have the 7 by 7 spatial neighborhood rather than having a single pixel time series as an input. And then I extract convolutional features which match information patterns that are found within this data cube. It was much harder to deal with in a sense that it was converging at a much slower rate than the usual 1D convolutional autoencoder. And performance-wise, when it came down to detecting fires, it was not as good. So the spatial temporal is here is in the middle, and so it's the CSTAE, and the fully temporal, which is the usual convolutional autoencoder, is at the bottom. It's FTAE, and you can see that performance-wise, relying entirely on one-dimensional convolutions allow for much better performance. At a lower training cost and at faster convergence. I assume it's because there's a confusion in temporally you have information that is much less impacted by speckle than you have at a 7 by 7 neighborhood way. Like in a 7 by 7 neighborhood, the most information you have actually could be summarized by an average intensity. And so if you were to train a model from scratch just to converge to computing the spatial average as an optimal weight, kind of troubles the gradient descent and kind of troubles the optimization algorithms, I assume. While directly focusing on, all right, we have this time series, find information within this time series without including some potentially additional noise, which is the spatial information. Turns out that it does converge better and it does work better. But I didn't put this to a larger extent than this context here. So but there might be some applications where it works much better than what I've done.
Okay, just I don't really remember, but at one moment you have one architecture where you have special convolutions which are pre-trained, and then you train the whole.
Yeah.
Is this one?
No, this one is another one. This one is what I called. This is just Frankenstein monster that I tried, which is I like to call the decoupled spatio-temporal convolutional autoencoder, where, as you mentioned, I've trained separate spatial autoencoder, which then I use to create, rather than input normal time series, having feature matched time series. And so it's exactly what you mentioned. This was kind of a madman idea, and I didn't really.
No, because I think this is the good way to do it, because the other one is too complex because it's 3D.
Exactly.
Here you split, but the problem with your choice here is that you pre-train the special part, and then you freeze it, use it as a feature extractor, while you could have trained the whole thing end to end. This is one of the questions that I had. I don't understand why did you split the spatial training from, you decouple the spatial training, decouple the dimension, this I understand because you reduce the number of parameters, so this is a very good idea. But decoupling the training, this I don't understand. You could have trained the whole thing end to end, because here you extract features which are not optimized for your autoencoder. You could have done the whole thing in one training. And you reduce the parameters with respect to the other architecture while having special features which are optimized for your task, your embedding. I think it's worth trying.
Yeah, I agree.
Okay. And then just one last question, and then I stop. If you go to slide 64, this is just one thing that I didn't notice when I read your manuscript and that I saw here. So actually what you're doing here so you have some kind of ensemble of models. You have several random forest models that you aggregate in order to being able to provide an uncertainty.
Yeah.
Why doing an ensemble of random forests which are already ensembles and which at the leaf of each tree, if you do regression, you have the variance. So just with one random forest, you already have your mean, which is the mean of the leaf of the trees, but you also have the variance. So I don't understand what do you gain by ensembling an ensemble model.
So the only thing is, so first thing, I use the random forest as an easy way. Other models could have been used as well, but they do behave well in such context. But all that being said, it's a very good comment. So mostly all of these random forests, they will have trained on different data. Because the first one will have trained on one specific split of one versus the rest configuration. The second random forest would have been trained on another split, and etc. So they all and in different information, and they all were, as they all have seen these different splits in the data set, they all have a different insights in the information content that this data set have.
I don't understand that, because random forest has a set of trees, and you use bagging, so every tree has already a different point of view on the data set.
It's true, but if you were to set aside I'm just justifying how the aggregation is relevant to this exact scenario, putting aside that we are dealing with random forests. But in the first case, as these models, whether they are random forest or not, will all have seen the different parts of the data. They'll all have made different predictions, and that's why gathering them together allows for some sort of uncertainty.
I understand the interest of ensembling, but when you have models which are not themselves ensemble models, so if you had used another kind of regressor, I would understand, but not for. But okay, okay. So thank you for the presentation. Thank you for the answer to the questions, and.
Thank you.
Thank you, merci. Now we will continue with Jeremy.
Okay, so first, thank you for the presentation and congratulations on the many contributions you made in deep learning in these 3 years. Many good ideas using autoencoders to detect not only anomalies in the data, but also in the labelings. It was a very nice manuscript to read. I also have a few questions. The first one I had was about why not using RNN and regularity, but my colleague already asked it. I'm going to move on to another one. Can we go to your slide 73 for illustration, please? Okay, so my first question is going to be on the clustering parts of most of your work. From what I understood from your manuscript and your presentation, pretty much every time you say clustering, it means that there is a k-means algorithm behind it, right? So the first question is going to be, why the k-means? Because I know that usually we use it because it's cheap, but since we have deep neural networks anyways, why?
It's a very good question. So first, I believe that the deep learning network will have done the heavy lifting when it comes down to extracting value and projecting the huge dimensional multi-temporal SAR imagery to this embedding space. And then you don't necessarily need the more elaborate clustering approach to kind of group your data points within the embedding space in relevant clusters, because semantically speaking, they are already kind of split one from another. We've seen it earlier with where I identified these mistakes in the cotton crops. We could visually, if we were to visually inspect, we could ourselves circle around some clusters by hand, because the projection of the autoencoder is efficient enough so that we just need then a method which picks the existing clusters within the topological space. But still, despite this kind of simple answer, I did some digging when it comes down to which are clustering approaches I could rely on. I found that, for example, I tried the DB-scan, which is very popular as well. But as soon as I was reaching, as I'm dealing with SAR time trees, I have often tens of millions of data points, and tons of these clustering approaches actually don't handle that well these dozens of millions of elements. And k-means, due to its simplicity, was kind of the only one to behave well in this exact scenario. And I really believe that this kind of curse of dimensionality is impacting most of the other clustering approaches. That being said, I didn't dive that much in diverse and various clustering approaches. I really relied on k-means because it proved itself as useful, fast, efficient, and cheap, as you mentioned, when applied to the crop types extraction. But as it's not really a core element of it is just there to prove that the embedding space contains the information I'm hoping to find in there. I didn't really spend too much time, but it's part of the perspectives to see, well, what if we were to use another clustering approach? Probably that the embedding space would be found to be even more valuable. So yeah.
I'm fine with this answer. One last on k-means. Did you have any trouble setting the k? Because we usually believe that k is going to be the same number as the actual classes. Usually it's not. So no, did you tend to have the k creators and the number of classes smaller? How did you handle this type of problem?
Yeah, I've tried. At first, I wanted to be a good student and do following some metrics. So I've done the algo method, trying to find a good compromise between the intra-cluster homogeneity and the heterogeneity between clusters. That didn't prove itself to be that interesting at the end, and so I just ended up using some rule of thumb amount of clusters depending on the information I wanted to find. If I wanted to split my data set in two classes, I didn't really need to rely on tons and tons of clusters. But when I need to split my embedding space in minimum amount of at least 16 crop types, I relied on much more amount of clusters. I believe I've written this parameter in the manuscript, and for example, for the case of agriculture, I relied on 100 clusters, which sounds like overkill, but it was the best way in making sure that even the smallest crop types, which don't have a big amount in the label count, will be retrieved, and that their retrieval wouldn't come from a limitation of the k-means algorithm. Because more often than not, the clusters tends to be of the same size. So as soon as you have label imbalance, they don't behave well. And so, but that wouldn't mean that the autoencoder didn't do its job. That would just mean that the k-means wouldn't be well parameterized.
Okay. My second question is still related to this type of architecture. In the same way that you were asked why separating the space and the temporal aspect. To me, you could have tried to go on a network from the beginning to the end. So instead of having some kind of Frankenstein monster with the beginning, which is a neural network, and then the clustering, you could have tried approaches such as deep embedded clustering. You mentioned, I think, in your future leads, maybe better loss functions. Well, actually, from your convolutional autoencoders, then using just back library optimization, you have the beginning of a clustering algorithm and optimization of the embedding space at the same time. So have you tried or taken a look at this type of approaches?
It's a very good question because I surely did, but I had tons of difficulty of making it work and converge because my first guess on this scenario of agricultural unsupervised classification was to rely on these models, on deep unsupervised clustering. Mainly the main idea was at each batch iteration you do an SVM decomposition of your embedding space and you try to optimize specific metrics so that this embedding space is directly clusterized. And I've tried this. It didn't work well, but I've not pushed it far enough. It's kind of, I feel like more often than not, my answer will be that I didn't push it far enough because this approach here, which is much more simple at first glance, reached more than satisfactory performance. But obviously, then it lags behind in terms of potential and complexity and still performance. So that's why I've assessed it, but as it didn't work well enough for me to dive into it deeper.
Okay, so maybe future lead of our next PhD student, deep embedded clustering for Gaussian mixture models. It's close enough from K-means Gaussian mixture models, so it should be working. Okay, moving on to the next question. When reading your manuscript, you had several parts in which you compared methods that were very different from one another. I think we have, for example, slide 32 and 52, in which we have random forest, we have PCA, we have CNN, one I think SA was shuffle attention or something like that. And my question was, do all of these algorithms start from the same basis? Because I assume that, for example, the CNN starts from the raw data, the random forest starts from some bottleneck of an autoencoder, maybe your CAE, maybe another one.
Actually, in this exact scenario, I've directly inputted the time series for the random forest, which results on surprising performance, meaning that it does beat the. But when I write CNN, it's actually the encoder part of my convolutional autoencoder, which I just reuse as a predicting model. So rather than having an embedding layer as a last layer, I just have a prediction layer where with my softmax activation and it just assign a class. So in this scenario, the random forests, all of them are
from the raw data.
They have the raw data as inputs. None of them is relying on non-raw data. I've tried actually combining the random forest with an embedding representation, embedding projection of autoencoders. And not in this context, but in the context of, if I recall correctly, classifying the land cover, forest cover, which I didn't mention in this presentation, but I mentioned in the manuscript. And I didn't find necessarily very good performance. But again, I could have dug more to make sure that I didn't over-parameterize or under-parameterize the random forests, because the amount of trees is actually a parameter that is critical when it comes down to good performance. So I didn't really focus much.
I asked because I was very surprised with the performances of the random forest, especially if you confirm to me that you started with the raw data. It's rare nowadays to see an old school machine learning algorithm outperforming neural networks. So
here I assume that it's also because we are focusing on this F1 score, and thanks to the design of the random forest being an ensembling approach, you could assume that separate trees would focus on predicting separate classes, while the convolutional neural network would focus on what brings the best in terms of gradient optimization, and often would focus on the labels with the highest amount of data samples. So overall performance, is lower because the CNN kind of like predicts very well the four most common classes, while the random forest also, thanks to this the ensembling approach, focuses on the much lower distributed labels. But that's how I interpreted this gap, because I do believe, and I do agree, I mean, that having a gap between these two approaches, considering the first one is supposed to be much better, is surprising. But it's how I interpreted it.
Okay, moving on to my next question. You used a lot of PCA to compare your autoencoder embedding with other things. Have you tried other projection methods? Because PCA is a bit the k-means of visualization. It's very old. As you said, it does not work well with nonlinear data. And you have cheap and effective other methods for data visualization that could have been tried.
It's a good question. I've not directly used the PCA for visualization purposes.
For compression.
But yeah, if I were to use it for, I just still bounce back on your visualization points. If I were to do this, I would rely on more traditional TSNE approach, which were proven to work very well for visualization's sake. Here, the key element was not necessarily to showcase the performance of the PCA, but rather showcase how well we would go when it comes down to linear decomposition of my input compared to non-linear decomposition with the autoencoder, and non-linear decomposition relying on convolutions with the convolution autoencoder. So I really see the comparison of unsupervised approaches as being each time one step closer to the best we can do, even if at the end of the day, the convolutional autoencoder that I design is pretty simplistic with regards to today's standards in deep learning, and there's much more steps to be reached. But still, I do agree with you that if I were to do some visualization of embedding spaces, I wouldn't rely on the PCA, as it wouldn't give the best results for this scenario.
Okay. You mentioned in your future leads that you wanted, for instance, to use recurrent neural networks, which for time series, I think would be a good idea. Did you have time to take a look at a few architectures that might be promising, and if you didn't test it?
I've tried the long short-term memory, which is the most classic one, I guess, in an autoencoding aspect, meaning that you have you apply this LSTM sequentially on all the inputs. You aggregate one of the outputs, one of the many outputs of the LSTM, and then you consider this as your embedding space, and you feed it back to another LSTM to reconstruct the original input. I've tried it. The convergence was not the best, not ideal, and this per se embedding space that I was generating was not perfect as well. So I've tried moving on to more modern approaches, such as the conv LSTM, which includes convolutions within the LSTM process. Wasn't that great also, but I do believe that it was just a question of trying out different parameterization and potentially different optimization objectives as well. Maybe for the scenario of LSTM, having a pure reconstruction-based approach in optimizing the network is not the best idea. Maybe an autoregressive approach by just seeing how well it predicts the next step in the time series would be much better in fitting the weights of the LSTM.
Yeah, or replacing the LSTM with getting recurrent units, which are simpler and sometimes have a better convergence.
Yeah,
Something to try.
It's true. I've not tried this one actually.
Okay, I have two other questions which are more generic, I would say. One thing that is very important nowadays when you develop deep learning models, no matter the application, is portability and how well you can use them in other scenarios. In your case, is there anything that could be reused for other forest problem, for other area, or do we have to retrain the whole network every time to fit the new area?
There is something actually pretty fun with unsupervised learning as a whole, is that if you were to use a randomly initiated neural network, it would still be actually good enough as a projection tool to extract insights from your input, because intuitively, even by having random convolutional filters, they would behave the same with regards to input that are the same or that share some specific properties. And so I would go as far as arguing that having a non-trained, non-fitted autoencoder would still be good enough to generate and extract some insights from an input data. And so due to the fact that it's not trained, you wouldn't really care that much about fitting it to new contexts and new data sets. But this is just some sort of like results with regards to the potential of non-trained approaches and randomly initialized autoencoder. I do believe that if you cannot apply the trained autoencoder in various locations over space, you can actually do it over time. It's one of the arguments I wanted to raise within the manuscript when it comes down to forest fire monitoring. You could imagine having, you want to monitor a specific area, so that's the limitations. But you want to monitor it all the time as long as possible. And so you would just retrain and refeed this autoencoder every time you have a new acquisition. And you would see how the last acquisition to date is deviating from what the autoencoder was going to expect to see happening. And this could very easily be done following the processing having introduced in this in the context of forest fire detection.
Actually, my question was more about avoiding to retrain the whole network. And
yeah,
of course,
okay.
If you could, in your case, could you imagine freezing the first layers of your network, which are usually the most basic features that you find everywhere, and only training the level above to have something faster and consuming less energy, less water, whatever you want?
It's actually a very good point. The feature extractor it's something that is pretty common in the field of deep learning, on relying on already pre-trained filter extractors and not bothering training them again, because more often than not, the people who trained them actually had more data on hand. So you would assume that the features are more performant than you would ever be able to get with your limited data amounts. So you could argue that freezing the convolutional layers would allow for some sort of no need of retraining the network whenever you dive into a new applicative scenario. So it's doable. I've not assessed how well it would behave, but it's surely doable as long as you have the same acquisition characteristics. I'm a bit doubtful if you were to have deviations in the amount of dates you have, the locations, or that the autoencoder would behave as well. But would it behave well? It's a very good question. It's very interesting. It would be interesting to assess.
Okay, last one, which is a bit more of an open question. In the title of your thesis, there is deep unsupervised learning. And you have worked a lot with data that were partially annotated, sometimes with annotation which were not perfect. So after this 3 years, what do you think of the unsupervised side of deep learning for this type of application that you dealt with?
So I think out of all the applications I've tried, there are two that really shines light on the potential of unsupervised learning. Even when you are in dealing with labels, if these labels suffer from quality issues, I believe unsupervised learning to be the best equipped to assess the quality of your labels and to find and identify label errors, as I've done it with agricultural application. Also, when your labels are insufficient, you would apply, strictly speaking, it's not entirely unsupervised. It's something called like weakly supervised, in a sense that you don't have that many labels, but supervised approaches would not behave well, so you have to rely on some tricks, including unsupervised learning, to extrapolate information out of a really small subsample of labeled data points. In these two contexts, I do believe that the future of unsupervised learning lies in the coming years and decades of remote sensing, because obviously we'll have more and more. We do already have tons of labels. Often lack quality, as I mentioned, our products are not that accurate. So if you want some predictions that are at a finer scale, you might often suffer from these quality problems. And I truly believe that just having as a quality analysis tool these autoencoders running on these data sets, you would be able to, on a local scale, identify and correct these mistakes to improve whatever application you want to be running in these exact locations.
Okay, thank you. I have no further questions.
Merci, thank you. Now we will continue with you, Robert.
Okay, thank
Please.
you. I'm going to ask some fundamental questions since this is not really my field. So you can have some practice at teaching someone who is eager to learn.
That's good.
What are the inputs and outputs of a CAE? Give me some examples of the inputs and outputs.
So in the scenario that I presented, you just have this Sentinel-1 time series. So you have variations of intensity backscatter at a specific location over time. This is the input, and the output supposedly is the same as the input. You try to have the output that matches as good as possible the input.
And what do you gain by matching it?
What you gain by matching it is as you went through a bottleneck in the middle in terms of dimension space, that means that this lower dimensional representation of your input has all the information content of your input, but is much smaller in size. So it's much denser in information. So it's much more viable as a tool for various applications, rather it is mapping, crop type classification, or forest fire detection.
So would a slope parameter be an example of an economy of?
It's a very good
example.
Yes, it's a very good point. In my perspective, I actually have forgotten about this, but the PNGG location has this slope issue, which we wanted to take into account when we were dealing with predictions of various forest parameters, to take into account the slope of the terrain. And this is indeed an input you could have to the autoencoder to guide it towards, this is the time series and this is the slope at the location of the time series. Do your best in encoding it to this lower dimension.
And have a reduced set of parameters. You have one slope parameter that can, say, goes over several hundred meters. So rather than give the value at each of those several hundred meters, you have one.
Yeah, you have one encoded representation. Yeah.
So, well, thank you for that. What is getting convolved in a convolution autoencoder?
So
is it the time series of observations past each other?
So for a single iteration of the network, you have your single time series, and you apply multiple convolution filters. And so, as I mentioned in one of the earlier slides,
does that mean the same size, the same string shifted in time?
Exactly. You have the same convolutional kernel that is shifted in time over your inputs, and it extracts by doing just some pattern matching what we like to call features, convolutional features, which are just the result for each time step of the convolutional operation. And by doing this multiple times, meaning that these results we apply once more some convolutions, and once more some convolutions, etc.
And you hope that you see a bump in this convolution.
You hope that you see some patterns. It could be a bump, it could be a gap, it could be a sinusoidal pattern, it could be anything, as long as this pattern was deemed meaningful by the network at convergence time. And this is entirely data-driven, meaning that if in all the data set, all the time series has, for example, a bump, that's not really informative because all the time series include this bump. But if a subsample of the time series includes some specific patterns, that means some information, some entropy lies within this specific pattern, and you want to be able to retrieve it. And that's how these convolutional filters will fit for the extraction of these unusual kind of specific features.
Okay, and in looking at your manuscript, I must confess to have only read about 60 pages of it, but the word deep doesn't appear except in the title. So can you explain to me what is deep? I was hoping to get it from your manuscript, but I think, by the way, I think you pitched it at the right level. Maybe the next paper I would love to see is one written for me, physics background. But what is deep?
We assume deep as long as you stack enough of operation layers, meaning that if you have just one convolution layers, it's not deep in the sense that the features you find are of the first order. It's just you match your kernels to your inputs, that's your output. This is not deep in the sense that you don't find more advanced features than what your convolutional kernels allow you to. But as soon as you stack convolution operations one after the other in the process of transforming your input, you reach what we like to call deep because you are able to extract more and more advanced features out of the original input.
Does that mean higher frequency ripples?
It could be higher frequency. It could be patterns that are not describable with just one kernel because you are a combination of multiple patterns. So that's why we also call it nonlinear. It's thanks to this stacking of layers that we achieve this nonlinearity. Because in essence, the convolution operation is purely linear. It's a linear mapping. But stacking them together and adding these nonlinear activations allow for mapping nonlinear patterns.
So deep means stacking more layers
yeah.
And thereby improving your resolution
and
of features you wouldn't see otherwise.
Also, yes, but also the complexity of the features itself. One great example that's usually shown more for image processing is just the first layer of convolutions will find straight lines. The second layer of convolutions will find straight lines that are crossing each other. The third layer of convolutions would map all the crossing straight lines together and be able to find all the windows within one image, basically. If you had only one convolution layers, you wouldn't be able to map all the windows. You would just be able to map all the straight lines, and that's just not enough. You need this combination of semantics to go from simple features down to complex features. So that's why it's important to rely on deep learning when you want to exploit as complex as possible features from your input.
So when you have simple features, it means that you're actually missing some aspect.
Exactly. Not, I would go as far as saying intentionally, because
but it's the price you pay.
Yes, exactly, for the simplicity. So it's an advantage in some way that it's easy to run, it's easy to apply, but you will not reach the performance you would if you were having more layers, which require more computation, which require more power, more consumption, but reaches better performance.
And so ultimately, you're minimizing a performance metric, right?
Exactly.
And is it that x minus ax squared? Is that what you're minimizing always?
In my exact scenario, yes. I've put in my perspectives that I could be minimizing something else, which would be, for example, a callback Leibniz loss, which would just check, okay, what's the distribution of your inputs? What's the distribution of your reconstruction? Are they matching? If they are not matching, could you try to make them match more? Which would not then optimize more brute force. This value is not matching this value. You need to do something about it. It's more, I assume that there will be some noise in the reconstruction, but at least is the general distribution the same. There are tons of objectives. All depends on the applications. But in the case of the autoencoder, the most common one is the one you mentioned, which is just to try to reconstruct the input from the input from the output. Using the mean square.
And are there, maybe you have this and I just missed it, but are there physical model based layers? Like I know when an area burns down, the general altitude of that, the phase of the, if you were measuring phase, is going to go down towards the ground as well. But that's bringing more knowledge to it. That you know that when the fire burns, the canopy altitude gets lower. Are there those kinds of inputs into your study, or do people use that sort of thing?
It's a very good question. I do not use it explicitly myself, but I've seen in conferences plenty of people in remote sensing conferences relying on what I like to call physics-aware neural network, which encodes some expert knowledge within the behavior of the neural network. In that case, for example, it could be that some specific phase change would imply some specific physical change within the monitor area. And so if you were to guide the neural network training by incorporating this expert knowledge from the start, you would achieve better convergence. But then you have another school of thought, which is just to say, let's just not guide neural networks at all, and believe that as it's a purely data-driven approach, it extracts all its inputs from data. The optimal weights it will reach is optimal with regards to the data, and we do not want to interfere with this process. It sounds almost religious in a way, but it's really various school of thoughts when it comes down to how to use deep learning models, and it goes far beyond remote sensing. I know in plenty of other physics fields, you have these continuous questions of, do we want physics-aware models, or do we want data-driven, purely data-driven models?
Maybe both.
Maybe both. Empirically speaking, sometimes one is better than the other, but there's no rule of thumb where every single time physics-aware is better than the other, or data-driven is better than the other. It all boils down to the application, I believe.
I wanted to bring up something which relates to what I work on, and that is three-dimensional structure. It's a very powerful index for what your data look like. And there are radar interferometers that give you this profiles of vertical profiles of the forest. And there's LiDAR, which gives you directly a vertical profile. And have you, does your plan for your future life include that? Maybe that's a good question. Are you interested in that?
I'm deeply interested in this. I've actually leveraged LiDAR data thanks to Andre, whom provided us with some LiDAR products. Among the scientific discussions we had was, we see that we are relying on neural networks and they are converging to whatever solution sounds the best. So what if we were matching Sentinel time series with LiDAR profiles using the autoencoder and see what's going on? Can we do a match? Can we do something? Because actually it's kind of handy. There are both sequences of data. And so you could extract insight from one to the other and vice versa. We've not done it, but it's interesting enough that we've mentioned it more than once. And I'm pretty sure that if any follow-ups on the forest studies, in particular in Parc National des Grands Jardins, that would be one of the next steps to do, trying to see how the autoencoder can extract value from both LiDAR profiles and SAR intensity profiles.
And the various data types, Sentinel, LiDAR, interferometric radar, they could, in a just world, could improve each other.
Yeah, exactly. Because you could have coincidental features happening in both of them that you wouldn't really pay attention to if they were happening in a single modality at a time. As soon as you look at the specific locations with more than one modality, you start to see the emergence of patterns that you just didn't pay attention to before. And I know that's why I truly also believe in the multimodality aspect of using convolutional autoencoder to merge information and data from various sources. It could be LiDAR, but it could also be optical imagery. I've never really mentioned optical imagery, but obviously it's really powerful, and merging this with radar would lead to much better performance, but also much more semantically relevant projections. So that's why it's something that is of high interest, including to me.
Could we look at page 25? This is just by way of amusement. I saw a pattern. No, that's not it. It's the one where you have the trace versus time. Yeah. What are those oscillations on the left? The big oscillation is summertime, right?
Exactly. Yeah.
And what are all those little ones in the winter?
So these little ones are just when you no longer have any crops. So you have ground that has been harvested, and so you have your ground, and usually what's being performed during the winter is just you have. I do not know the English words for it, but you just you have your flat terrain and you roll your tractor into it, and
so that's the spatial frequency of tractors.
And I just believe that There is the impact of soil, of ground freeze as well, because we still reach below 0 temperatures in some places. I didn't include it here, but we have also rice crops, and the rice crops can be flooded in the winter. But the fact that these patterns emerge across every single crop types really shows that it has something to do with the state, the conditions of the ground after the crop has been harvested. So that's why I first mentioned this aspect of taking care of the soil, but it could be plenty of other things. But it's a very good point, because we did ask ourselves the question: what if we were only to focus on the summertime? Because obviously it seems like these winter acquisitions are not that informative when it comes down to modeling crop types. So what if we were just to focus on the summertime and see the performance? We've mentioned it, we've not tried it, but that would be a next step, I assume.
But the oscillations are universal, though.
Exactly.
In everything. Could it be instrumental?
They appear to be too much in decibel values to be instrumental. And the fact that they're universal, I believe, has more to do with the fact that all the crops are in the same conditions. Because you have one standalone, which is, for example, the sugar beet, which grows during early winter. And so obviously you don't have the same oscillation patterns that you have on every single crop type that doesn't grow in the winter. So that's why I really do believe that it has to do with having some empty agricultural areas rather than.
These are all from the same latitude, right?
It's the same. Yeah, it's the same locations. It's fairly large agricultural area, but it just spans at best 10 kilometers wide.
I think it depends on the soil moisture, because I think during this period we have rainfall. With the rainfall, we have the soil moisture increases. For this reason, the radar signal increases. For this reason, the main fluctuations correspond to the increase of the soil moisture.
Because of rainfall.
Yes, exactly. Sure.
So if you looked at the rainfall plot and the same thing, you would see the wiggle.
Yeah.
That'd be great.
Yeah, sure. For me, for example, between October and December, I'm sure the main fluctuations correspond to the increase of the soil moisture.
So I would never have guessed it'd be so periodic. There it is. Well, thank you.
Thank you very much.
Thanks for the supplementary teaching.
My pleasure.
Okay,
No,
thank you.
That's all.
Okay, for me. Thank you, Thomas. I have some short questions, because the main questions were proposed by Robert and Jordi. My first question concerns the use of several orbites. If I understand, you use descending and ascending orbites or not?
No, I rely only on one specific orbit.
Only one?
Yeah.
And you select this? How you select this? Because why? Because in Europe, I think for your small study site, I think you have between 3 and 4 orbites, 2 ascending and 2 descending. How you select?
So it's a very good question. A very empirical way of doing it. I just take the one that has the most amount of data points.
Okay, you select one.
Yeah, I select the one with the most acquisitions, just because I want to have the most information. So, but outside of Europe, you are, for example, in Canada, I didn't really have the choice. I always had just one configuration to deal with. For example, in Hay River, if I recall correctly, it's an ascending path, and it's the only one available. In PNGG, the second test site, it's a descending path, and that's the only one available. So each time I was not forced, but just I didn't really have a choice. In Europe, it's different. I'm just relying on the ones that have the most amounts of timestamps.
Okay. My question, for crop application, I think we don't need very dense SAR time series. For this reason, we can use, of course, we can use one orbite. Why not? But the main question for me is, for each orbite, we have a given incidence angle, because the incidence angle is not the same for each of these orbites, and the dependence of the radar signal on the dependence of the radar signal on the incidence angle is not the same for each crops. For this reason, maybe for some crops, it could be better to use high incidence angle, and for some crops, it could be better to use a low incidence angle. You see?
Yeah, it's a very good argument. And I would go down the road of saying that if we were to use all the orbits together at the same time, the convergence of the network would lead to exploiting the orbit that is the most optimal in isolating whatever crop type we're focusing on. So that would be a very good argument in saying that let's just give all the data we have to the network and let it deal with it, because by the sake of optimization, it's supposed to find the best configuration possible for the given application. So it's a very good argument.
Okay. Next, I will continue with the question proposed by Robert concerning the slope. I will not suggest the slope. I will suggest the incidence angle or the local incidence angle, because the local incidence angle combines the incidence angle with the slope. So, for example, if in operational way, if tomorrow you will apply your classifier for vast, for wide study sites, for this reason we will use the wall of incidence angles and the wall of Sentinel-1 images, right? So the incidence angle will be different between the first pixel and the last pixel. In this case, if you need to modify your classifier, what do you propose in this case? Because the input you will modify the input or not?
I would modify the input, but post convolutions, because I assume that the incidence angle, as long as you stay in the same orbit, will not change over time. So you don't necessarily need to find temporal features from the out of the incidence angle, but you still want to include it in the computation of the embedding space. So I would add it between the convolutional layers and the fully connected layers as an additional.
You will add the incidence angle in the input file. No.
Yeah, I would.
If we assume we use only one orbit, only one. For only one, okay. The problem is we have not the same incidence angle for all pixels.
Yeah.
In this case, it is necessary to associate to your radar signal the corresponding incidence angle.
Yeah. And this problem would really arise when whenever you are manipulating full swath, like you range from the eastern to western side of the swath, and I agree, and we do visually see that it does have an impact on the SAR image, and so that's why, as I consider it to be over time a stable parameter, but it doesn't change. I don't think that adding it alongside time series right at the input makes sense, because the convolutions wouldn't find any relevant features. But rather adding it at the interstice between convolution and fully connected layers, meaning right here, would make more sense. And then it would be processed by the fully connected layers of the encoder and be embedded within the embedding layers. And then I do believe that it could add some value, because it would debias the potential incidence angle bias. A way of doing this also would be to rely not on sigma naught, but on gamma naught parameter, which no longer is tricked by the incidence angle. It could be another way of doing it. And I know that, for example, my colleague André Baudouin is relying on this when he's dealing with Canadian forest monitoring.
Yes, sometimes we propose to use the gamma naught, but the problem is in agricultural area, I'm sure the gamma naught is not the best solution. Why? Because the gamma naught is the sigma naught normalized by cosinus theta. And for crops, it is not cosinus theta. It could be cosinus square. It could be etc., etc., etc. And the power of this cosinus is not the same for all crops. For this reason, it is not easy to normalize the radar signal by cosinus theta or by cosinus square, etc., etc. For this reason, it is not easy. In forest, maybe it is more applied because we use gamma naught, Sometimes we normalize by cosinus theta. Sometimes we normalize by cosinus square theta. But for crop, for me, it is not relevant to use gamma. Maybe the better is to use the incidence angle in the list of input parameters. Okay. My second question concerns the transferability of your classifiers. My question concerns the crop application for the moment.
Okay.
If I understand, you use data set only for 1 year,
Yes.
2017, yes?
Yeah.
You have not another year, no?
No.
No. Okay. Have you an idea about the temporal and spatial transferability of your classifiers? Temporal is when you apply the classifier for the same study site but for different years, and spatial when we change the study site, not completely. We are in Europe, we stay in Europe, you see.
It's a very good question. I'll just directly put this slide. So first thing, I'm using 1 year of data, obviously, because I assume that my crop rotation cycle is 1 year. Not every crops and not every agricultural areas will follow this, and so the transferability of my approach is a direct function of this crop cycle rotation. But this, let's consider that we are always dealing with crop rotation cycles of 1 year. I believe we might struggle in direct application of the autoencoder for the reasons that Robert pointed out actually in the first place, which are these the patterns, temporal patterns that are non-related to crop types. And because you could assume that whether cotton grows 1 year or the other, as your convolutions are invariant to shifts, if the growth is a bit early or a bit late, shouldn't pose any problem in diagnosing that you are dealing with cotton. But these phenomena, which are highly punctual if it relates to soil moisture, will have a significant impact on how your time series will look depending on the year you're manipulating. And so I do believe that transferability over time may struggle due to this. Multiple way of fixing it would be, the first one would be to only focus on dates that actually are relevant for crop type classification. If you only focus on summer dates where you know for a fact that something is growing, you would have very good transferability because as long as you remain in the same crop types and they all grow during the summer, aside for sugar beets, all should be good. But if you were to use the full time series, I'm not entirely sure that it would behave. It would behave good, but maybe not as good as applying it on the year you trained it, obviously.
Okay. We continue in this way. You think your classifiers perform if we have small shift in the growth cycle, for example, or first question. The second question is, you think your classifiers could perform if, for example, concerning the cotton, we have the main peak, the characteristic peaks. The problem is between 2 years, the duration of this peak could be different because the temperature is not the same, rainfall, etc., etc. It is the same if we change slightly the study site. So my question concerns this one. You think your classifiers could perform if we have a small shift in the cycle, in the growth cycle, or if we have some variation in the duration of the characteristic peaks of some crops?
It's a very good question. I would believe that as long as the maximum matching likelihood between the cotton at year 1 and the cotton at year 2 where you had this shift is achieved, as long as you have the best matching profiles of year 1 are with profiles of cotton in year 2, no matter the transformation they suffered. The convolutional autoencoder will keep on behaving well. The thing that will start to pose issues would be if confusion could arise between crop types due to these shifts in their signatures. But looking at the plots here, I assume that you would always find patterns that are specific to cotton and that would only be identifiable within cotton crops. And it could be as small as, for example, here, these small decrease, these small spikes followed by decrease, followed by increase of signal, which are only really found in cotton, no matter if this part of cotton harvesting happens much later or earlier, or this part of cotton growth is slightly shifted. As you have these like specific localized patterns that are specific to one crop type, you should be able to retrieve them as good as the year before, maybe with some performance decrease, but not to a large extent. But this, again, is an assumption. And the second part, which is very interesting as well, is a given crop, like this is just cotton in general, but obviously not all the cotton crops undergo the same agricultural and harvesting practices. Some may be harvested much earlier, some may be completely rotten and dried out and non-usable, but they still all belong to the same class at the end. And this boils down to modeling what I like to call the intra-class variance, meaning that within a single class of crop types, for example, here cotton, you do have variance of profiles. It's natural. And I've actually investigated this with rice crops. And I've shown that the application of autoencoder on rice crops was able to retrieve these variations in harvesting practices of rice. The key one being that during the winter, you have this optional choice of farmers to flood their agricultural crops. And then they get some financial stipends from the local government. It's another story, but as it's an optional process, not all the rice crops will look the same during the winter. And so you have this diversity of temporal profile, despite all the crops being labeled as rice. As I've seen that the autoencoder is robust in a way that it encodes this diversity in a kind of hierarchical manner, I forgot to put this in perspective, actually. In kind of hierarchical manner, it should behave accordingly to plan, I believe.
I have another question concerning the forest part. If concerning the estimation of the canopy height and the biomass, have you the scatter plot where we can see the estimated values according to the in situ measurements or not?
No,
because you give the R square.
Yeah.
But in the manuscript we have the correlation between estimated and in situ measurements.
It's true.
You have none.
But I've done it.
But it is included in the.
I don't recall correctly whether it's included.
If I remember, no problem. If I remember, the correlation is bad. You confirm or not?
Of the tree heights?
Yeah.
Yeah, the correlation of the tree heights, but I believe you're referring to the one that is extracted from LiDAR data. I understand that it's quite confusing because the regression results I've shown in these slides are not in the manuscript in the sense that they came kind of after the end of the manuscript writing. So they are kind of new. The results you're mentioning are the ones related to the LiDAR products. So we had this LiDAR mapping, and we were trying to predict LiDAR. I can actually display.
When we see the curve, the estimation saturate very quickly.
Exactly. Yeah,
yes,
exactly.
You confirm.
Exactly.
Okay. So the question is, we have saturation because the data set used in input is not relevant for this application, or because you have very small data set, because if I remember, you have less than 100 points. And I continue my question. In this case, I continue with the question proposed by Robert. In this case, why we have not used, for example, GEDI data in order to increase the number of, it is not in situ measurements, but you see?
So it's a very good question. So first, the results you're mentioning.
You see, this problem, you understand?
Exactly.
The main problem is, it is bad because the algorithm is not relevant. It is bad because the data set is not consistent.
It's really.
Why? Because I continue because sorry, because in the literature we observe many papers where the authors use Sentinel-1, use Sentinel-2, and the correlation is better than this one. But the algorithm is not the same.
Yes. Part of the two, the culprits are both, I assume. The model is insufficient in the fact that it's unsupervised, and so it's not optimized with the objective of retrieving whatever regression model or regression parameter we want. The bad canopy height retrievable metrics we have are based on trying to predict this. So this ground truth, which is a ground truth made using airborne laser scanning data, which I didn't mention really in my presentation. The performance is pretty bad. It's like 0.33 or even lower. Like it's really pretty bad. I've tried retrieving this using purely SAR metrics, no deep learning, and that's the last chapter of my manuscript actually. And what I've seen, so I'm sorry for the ugly plots. So this is the canopy height retrieval using some parameters that I extracted by hand from a time series. And we have the same saturation phenomenon happening when it comes to the prediction of the canopy height. We see that the canopy height is on the x-axis, and whatever parameter I use is on the y-axis. And we very quickly see that the canopy height prediction saturates to a point where it's linear with a function of this parameter. And this, I truly believe, as I've not used any model and I've just used the input data, which is Sentinel-1 time series, and this comes down to Sentinel-1 limitations. You can go only up to a certain point when it comes down to inverting specific forest parameters because you have physical restrictions of Sentinel-1 data. You mentioned earlier that some papers were combining Sentinel-1 with optical imagery.
Mainly the authors use UNet, for example, or transformers. And the results are very good.
Yes, but
are very good. Are good.
You may notice that actually I've not found a single one relying entirely on Sentinel-1. Every single time they are relying on a combination of Sentinel-1 and optical imagery. I do believe that it's because of the bottleneck of Sentinel-1. You cannot achieve respectable enough performance. You will always have this C-band bottleneck, physical limitations of the sensor. I actually struggled when building my bibliography, trying to find times where authors would only rely purely on SAR information. Every single time they are really combining information from various sensors, and so it's kind of hard to say what's the potential, the limits of the applicability potential of Sentinel-1, because every single time its performance is measured alongside optical imagery. And here in the last chapter of my thesis, it's precisely what I've tried to do. Setting aside all deep learning models, what's the data limitation when it comes down to forest parameter inversion? And in the case of canopy heights, I've seen that any tree above, 5 meters, you cannot differentiate them using Sentinel-1 data. They all look the same, basically. But key fact here is that any tree below 5 meters, you can actually differentiate them using Sentinel-1, and it's still a good enough results because it's C-Band SAR. You have it over the whole world. It's open data. It's the only satellite that has this configuration, so it's still good enough results. For canopy cover, the performance was actually much better. I don't know if you recall correctly, but in the manuscript, I've shown that canopy cover is pretty well retrieved from Sentinel-1 data. And so that shows that not all forest parameters are equal when it comes to sensor limitations, and some are much, much better retrieved than others. And it all boils down to the same question of what the sensor limitation actually looks like. in terms of physical interaction of the incident wave with the monitored environment. And I do believe that the canopy cover metric is much more Sentinel-1 compatible in terms of parameter than the canopy height.
Okay, thank you.
Thank you.
Merci. Donc, we will continue with André.
Yeah. André?
André,
Yep. Yeah. Can you hear me?
Yeah.
please.
Okay. Thanks. Thanks for a nice presentation, and actually the quality of your English speaking. It's better than mine, actually. And I appreciate the new elements in your presentation compared to your manuscript. So it does provide additional insights in your work, and I did appreciate that. I'm coming more from an application perspective, and my questions will be along operational perspectives and constraints, because in Canada we have 6 million square kilometers of forest, and there's a lot of disturbance going on. And as you know, last summer it was the worst ever fire season, and 18 million hectares did burn from May to October. So my questions will be related a bit to this kind of issues we have to monitor our forest, and considering the fact that so far we've been able to map and monitor forests with optical data with pretty good accuracy for mapping various attributes like height and canopy closure and so forth. And we're able to map harvesting and burn area with still optical data with pretty good accuracy. So having that in mind, and you've answered a bit about that, can you further summarize, the limitations of C-band data that you've mentioned pretty late in your presentation? So we just talked about that. So can you provide to me 3 key limitations, and to which point your temporal approach using CAA can circumvent some of these limitations? And again, in a Canadian context, and what I've forgot to say is that we have as well forested areas over very hilly terrain, which is an issue.
Which is a critical issue.
Yeah.
I'm sorry, you finished?
Yeah, sorry for a long introduction and question.
So thank you for your question. It's a very good question. So the assumed limitation of C-band has to do obviously with the frequency or wavelength of sensor, and its sensibility to smaller elements of trees. Mostly when we are looking at trees in Canada, the interactions of the 5.4 gigahertz of central frequency satellites will be with regards to small branches, small leaves, which do not tell us much when it comes down to large physical attributes such as canopy height, canopy cover, tree height. For biomass, it kind of sounds like good, but as there's no great penetration properties of C-band, it sounds like it's a largely limited approach.
Okay.
The thing is, and you've mentioned it, as soon as we switch to temporal analysis, it's been proven actually for quite some time now, since the late 90s, by researchers from JPL, that you are able to extract the ground state, whether the ground is frozen or not, using C-band multi-temporal data. If I recall correctly, I believe it's with ERS-1 satellite. And they use time series of like 6-7 acquisitions, and you're able to tell the condition of the ground. So that assumes that the incident wave, C-band incident waves, still has some penetration properties in the fact that it does reach all the way down to the ground to retrieve this ground condition information. And this only comes true as soon as you start to look at temporal evolution of the C-band signal, because the relative change in the signal over time is a direct function of the condition of the monitored environment, which includes the ground. If you're able to reach the ground, you're able to kind of invert a function of how much of the incident wave is reaching the ground. And this in itself is a direct function of the physiology of your forest. And it's why I do believe that temporal approach in assessing the potential of C-Band SAR would allow for much more accurate applications of forest parameter inversions. And so yeah.
Okay. You've included in manuscript an approach to determine what are the most important acquisition dates in your time series. Yeah. Can you say a bit more, because it relates to what you've just said about, winter imagery and frozen ground versus unfrozen ground. So in other words, how your tool could be helpful to, instead of synthesizing all the time series, maybe just pick up the best dates that would provide the best predictions with whatever, prediction modeling approach.
It's a very good point. So unfortunately, I've forgotten to. So that's kind of unrelated, but I've forgotten to add additional slides discussing this. But one of the key insights in trying to explain what's going on with autoencoders was to be able to set an importance value for each of the single input of the time series, if each of the temporal acquisition of Sentinel-1, and to decide how important this acquisition is for the generation of the embedding space. The intuition being that these dates are the dates where most of the information is contained when it comes down to identifying crop types, identifying forest fire, or in a case here, inverting forest physiology. When applying this approach to the case of inverting forest physiology, something very interesting appeared. It was that during the winter acquisitions were the most critical for the inversion of forest parameters, as long as you are dealing with C-Band SAR time series. And it appears that I've kind of dug much more into this. I believe that more answers are present within the last chapter of the thesis. But digging into these winter acquisitions, turns out that the change in the soil condition has such an impact on the temporal profile of forest that by measuring some specific features, patterns within the time series change, you can go all the way back to the physiology of the monitored forest. And I wouldn't have had this intuition without leveraging this explainability tool applied to the time series that were processed by the autoencoder. So it's a very good point you're raising here, André, that one more usage of the autoencoder for scientific purposes is the identification of patterns within a large data set, which would take weeks of investigations if done by hand. So in combination, the combination of the two allows for kind of like a fastened appreciation of the information content of an unlabeled data set, and help whatever scientist is doing what he's doing focus on the specific time frame that is the most adequate for the application of interest. And this is something that goes beyond just applicative potential.
Yeah. So we're back to one advantage being a good exploratory tool.
Exactly.
Yeah, because another example is that we found out by accident that, it's already known that when you're getting to the spring season, when you have melting snow background, you get the greatest sensitivity to forest attribute because of the range of the backscatter is the widest possible between no trees and fully treed forest cover. So this kind of tools could be helpful to find out these kind of conditions that otherwise are difficult to find out at the large scale, but because you would require weather data and so forth. So that's interesting. Now, this slide is leading me to the next question about your approach to handling and synthesizing time series versus ours, which is very much simpler, but with the benefit of greater explainability. So if you look at your profiles on the left, what we've been using to synthesize time series, using the same area, the same plots then for predicting attributes, you see the seasonality. It's well known with optical data because of leaf on, leaf off, and phenology and so forth. But we observe this cyclicity here. And what we did is to use either simple temporal stats across the time series combined or not with harmonic fitting parameters. And we found out pretty good fit. And out of the harmonic fitting, we've used the amplitude, the modulation, so forth. And at the end, we've got much more better predictions using these parameters than using usual summer or winter temporal composites. With the advantage of explainability, because we can relate the modulation to variations in, soil moisture content, snow versus no snow, cover on the ground, so forth, in liaison with the scattering mechanism. So, and we've got pretty good R-square using simple random forest predictions. So I'm wondering about really the benefits of your CAA approach when trying to exploit that for very large scale mapping in terms of computational efficiency, and the fact that it's hard to explain with physical basis or scattering mechanism the results compared to simpler approach. So what's your take at this point on the cost benefits of your approach versus simpler ones for large scale mapping application?
It's a very good question, and it's a question that spans over the entire area of science as a whole. Is deep learning in general does not replace expert knowledge in does not replace expert knowledge at all, but in not in all situations. In this exact scenario, it will not replace expert knowledge when it comes down to appreciating the information content of SAR time series. The only thing it does is give insights, hints on patterns that lies within the data set and that are worth exploring. And then the exploration task is simply handed over back to the scientists who has these insights that are purely data-driven, meaning that we found these patterns within the data. We've extracted them from the data. It's worth investigating. There's something there. But it's never the end results. It's never the end of it. It's just a first initial step, which very often I find could be pretty time consuming, especially when jumping into an area you don't really know. It's my personal experience of driving the autoencoder around various application areas. It's just I was never really familiar. I've never been familiar with forestry at all. Applying the autoencoder to a pile of multitemporal imagery acquired of a forest helps me to gain some insights on what are the key elements that are the most decisive when it comes down to how the forest will look like, what are the key dates, what am I supposed to be looking at within the forest. And all these insights are purely extracted from data. And this is what I believe to be the power of such approaches, which is to give not only a shortcut, but also sometimes to raise concerns, ideas, to provide hints and insights that could have been unsuspected until then.
I like your answer because, I think there's increasingly raging debates between, two schools, the one being, full deep learning approaches without any considerations for explainability versus maybe a bit more old school, physical based modeling. And I think here you're showing that we should kind of bridge these two schools, and your answer for me tells me that you're aware of the need to kind of reconcile these kind of complementary approaches instead of antagonistic approach that we witness sometimes in conferences. Other questions about, fire detection is a big thing, as I mentioned, in Canada. We've considered Sentinel-1 for a while because of dense time series, but with the data of Sentinel-1B and waiting for Sentinel-C, plus the fact that the fires are very big now. You know, typically they have 500,000 hectares. And we don't have a large swath with Sentinel compared to, for example, our Canadian radar sat constellation mission SAR mode with 125-kilometer wide swath. So now we're switching gears, exploiting compact pole data from SAR RCM data, because they've started to build through background mission acquisitions a time series of these data at 30-meter resolution. So what's your take on your approach being eventually adapted for such data, knowing that so far we don't have that much dense time series because they've started archiving such data only since fall 2022. In other words,
yeah.
When you think CA is useful as a rule of thumb in terms of the density, the time density of the stack, you know, if you just have 10 scenes, is there any usefulness compared to what we've been doing so far, is just getting the best pre-fire and post-fire image and get burn indices from the pair of images? Do you see any benefits in this approach for mapping burn area using a short time series of RCM SAR data?
It's a very good question. So I will answer it in two parts. First part being that convolution autoencoder does handle short time series. In the manuscript, I've manipulated short PSAR data, which are not large time series. We just have like 7 acquisitions, and they still were able to retrieve targets that were hidden under vegetation canopy, despite this short amount of acquisitions. The only thing is you need to change the design of the autoencoder to have convolutions that span much less over time, that do not reduce the temporal dimension along the layers. But all things considered, you could have a workable autoencoder that would be compatible with the system you are mentioning, the configuration you are mentioning.
Yeah.
On whether it's relevant or not, it's a very good question. Yeah.
Go ahead. Yeah, sorry.
Yeah, I would say that one key thing that the autoencoder is bringing to the table is that even if I've used it for binary kind of applications, meaning that, okay, I'm predicting fire versus non-fire, I'm predicting cotton versus non-cotton, it actually is much more than that. The embedding space is a continuous valued space, and you could have information related to fire severity, hopefully. You could have information related to the conditions of the burnt forest, because saying that the forest was burnt, and you're well aware of this, is not informative enough to know the conditions of the forest. Some trees might just have their branches being burnt, some others might just be burnt to the ground, and this, I assume, could be found within the embedding space of convolutional autoencoder, while it wouldn't be easily found in the post-pre-fire image ratio. Again, I'm not that familiar with this approach. I'm just assuming that one key benefit that could be taken out of the application of the autoencoder is the fact that the embedding space as a continuous space can represent much more than just burnt versus non-burnt.
It's a good point, because you know, we need just burn area monitoring during the wildfire season for following up critical wildfires, but then burn severity is required as well for post-fire, you know, forest management and so forth. And it's a good point that probably your embedding space has more information richness compared to just a pair of pre and post-fire image. I'm mentioning that I'm asking this question because now, since we have 3 radar satellites, we are able to task these 3 satellites in emergency mode, so we can get 4-day repeat revisit time of a given wildfire, so we could build denser time series. So I think there are good perspectives here about this approach. 2 last quick questions, because time is running. Yeah, it's been mentioned that, and we've found the same thing, that using Sentinel-1 alone even with time series, does not provide much as good prediction performance than using time series Sentinel-2. And we've looked at comparing Sentinel-1 base versus Sentinel-2 base prediction of a suite of attributes using random forest. And when combining Sentinel-1 and 2 time series matrix, we don't see much improvement. So the benefits of adding Sentinel-1 Sentinel-2 is not that great. So, which is a bit sad in a way. But then that's a perspective questions. You know, that's NISAR is going to be launched, and we could have L-band data at 12-day revisit time, probably sometimes next summer or next fall after the commissioning phase. So what do you think you would gain using CAA exploiting L-band time series compared to using C-band?
It's a good question, and it's
you think it would be a game changer for forestry applications?
I assume it would. There's also the when it comes down to vegetation monitoring, there's also the biomass mission, which should come anytime soon, hopefully. And all these missions that are much more designed, much more calibrated for vegetation, forest monitoring in particular. I'm mentioning vegetation, but here it's really for forest monitoring. They will bring to the table much better value in terms of data, and the insights will obviously be much better. I'm not really familiar with the current running SAR mission in terms of temporal density. I do not know that well how many acquisitions there is, but I do believe that NISAR will bring such a change in the sense of the amount of temporal data you have with an unprecedented configuration, because it also embarks, if I recall correctly, a second sensor, like it's two sensors configuration, LNP band, if I recall correctly. S-band. And the combination of the two would that would be not only a game changer, I truly believe that would be a game breaker. And I'm really looking forward to seeing how the time series are going to be looking. And well, that kind of matches my perspectives of applying the autoencoder to new configuration and new sensors, because I'm eager to see how it would behave with the NISAR sensor. I've delved into the intricacies of Sentinel-1 imagery for too long. I'm really curious of seeing something else, and I do believe that this is the next step towards more automated monitoring of forests. Because the end application is this, like for science sake, it's great to see what we can do with combining specific data with specific algorithms, but for application sake, and it's the natural resources Canada priority, it all boils down to what we're able to be doing. And I truly believe that the limitations of C-band are too big to be alleviated simply through more complex algorithms. The only way to alleviate them is through more adequate sensors. So that's why I'm really enthusiastic when it comes down to the NISAR launch.
Yeah, I am as well, especially when combined with optical data, because so far we've relied on PulsAR data. It's just that it's a pity that we don't have access to the full archive, except for PIs, and so we just relied on annual global mosaics, which we don't have the control on the acquisition dates. But still, we've done something with it. But PulsAR combined with, NISAR time series combined with Sentinel-2 time series should be a game changer, especially using more advanced, approaches like deep learning algorithms and so forth. So we're very excited about the following years and the exploitation of such data. So I would just like to finish saying that it was a great pleasure being a collaborator, great fun, either during field work or when we exchange about our different approaches to estimate the forest parameters. So good job, and good luck for your career, and I'm pretty sure you have good opportunities ahead of you.
Thank you, André. Thank you. It was a pleasure collaborating with you as well. Thank you very much.
Yep.
Merci André.
Merci.
On va continuer avec Élise. Quelques commentaires sur la thèse de Thomas.
Je passe en français ou en
Comme tu veux.
English, as you want. So just, I would say congrats, Thomas, for your defense and all your PhD work. It was really a great pleasure to have this opportunity to co-supervise your PhD thesis. And I would just mention that what was very great was that you were always enthusiastic for all propositions that we made all together. And you didn't mention, for example, the whole contest you participated, of course. For example, as soon as I proposed you to deal with the Sentinel script contest, you participate, you win. The same with the IEEE data fusion contest, of course. As soon as we discussed together and we decided to write a paper, you write it. So it was for us, it was perfect. For you, it was perhaps a little bit difficult because we didn't help you to find a common direction. So it was a great difficulty in your case to make the choice of a specific line, scientific line to present. It was very difficult. You did it. So thank you for everything, and everything wouldn't have been possible also without the help of the Sondra Lab. So
yes.
Thank you also to the Sondra.
Thank you. We'll continue with Laetitia.
Yes, so